resource person of the program, Dr. P Sankar sir, Assistant Professor from NIITAP, and all the participants from ACTE approved institutions and all the participants from our host institution and our organizing team. A very good morning to one and all, and welcome to 2-week faculty development program on artificial intelligence based energy storage system integrated with renewable and sustainable energy sources for electrical vehicles. As per the instructions from the ACTE Training and Learning Academy, we conducted 13 sessions till date. In day 1, we conducted 2 sessions by the resource person, Dr. K. Reddy sir, Professor and Head of the Department of Renewable. In day 2, we conducted 2 sessions by the resource person, Dr. K. Reddy sir, Professor of Renewable, JNPT, Andhra. Day 3, we conducted 3 sessions by the industrial expert L. Sastry from the Rolling Technologies Private. And day 4, we conducted 2 sessions by the resource person Dr. P Sankar, Assistant Professor, NIITAP, Andhra Pradesh. Day 5, we conducted 3 sessions by the resource person Dr. D. Srinivasarao, Associate Professor of Renewable, NIIT. Day 6, we conducted 2 sessions by industrial expert Sri Uma Deshmukh, Chief Artificial Intelligence Officer. We need to conduct another 3 sessions, and we need to conduct 4 days industrial visits to complete our 2-week ACTE sponsored faculty development program. This is the current status of our faculty development program. I request our organizing team to introduce our resource person for the program and start the program.
A very good morning to distinguished guests, esteemed faculty members and my dear participants. A warm welcome to Day 7 of ACTE sponsored ATAL FDP on artificial intelligence based energy storage system integrated with renewable and sustainable energy sources for electric vehicles. Today, our resource person is Dr. P Sankar sir from NIIT Andhra Pradesh. Coming to the educational qualifications, he has his PhD from National Institute of Technology, Tiruchirappalli, and MTech from Acharya Nagarjuna University. He has worked in various colleges and NIT Calicut. He has around 10 years of teaching experience. He has published various patents and papers. Coming to the administrative responsibility, he worked as the head of the department in electrical and electronics engineering during 2018 to 2019. He also worked as associate dean research and consultancy from 2020 to till date in NIT Andhra Pradesh. He has the ongoing projects on establishment of common research and technology development hub in renewable energy sector sponsored by Department of Scientific and Industrial Research, Ministry of Science and Technology, with a rupees of around 7.15 crores. He has completed projects on pumping system using multi-level inverter from SET, DST Government of India with a grant amount of rupees 20,04,970 rupees. So now I request Shankar sir to please start today's session. Welcome sir.
Of PV systems. Of course, PV and EV both, like I talked together. So both photovoltaics and electric vehicles. Like what are the opportunities and what we actually look as a power electronics engineer. I think a few resource persons they might have also covered few aspects, but maybe you can just try to. I will be going more into the fundamental aspects. The more fundamentals is always good. So I request you be attentive for this workshop. Try to get something out of it. Okay? You learn something. That's a motive. So, what is this learning? You know, these days there are two important technologies, especially we have to own electrical engineers. I think all of you are electrical engineers. So how to own the two technologies. One is electric vehicles, other is renewable energy. Okay, these two are we should own it. Okay, so see, like why we need, because you can see one minute. You put pencil. Yeah. In case of electric vehicle or in case of renewable energy, these two are two technologies people are talking about. And there is a huge opportunity for EV and PV photovoltaics. In future, like electrical engineers have a lot of room. Anyway, so coming to the importance of power electronics. Before doing that, so just I want you to understand what, like some background. Okay, so what is this one? This one, like solar irradiance and wind speed. I have just shown you. So one is the down is the solar, the down is the wind speed, and upper one is the solar. Okay. What is this? Like what is the fundamental understanding of taking from this slide? Is the irradiance is not constant. The solar irradiance, it is constant. It varies actually with respect to like day, during morning times you have one irradiance, during afternoon you have other irradiance, sometimes clouds come into the picture. So like if you see a particular data like of a complete day with respect to like irradiance is plot, it is not a fixed value, varies a lot. Similarly, a wind speed also varies. Per day, if I show you per day irradiance, you can see a typical per day irradiance, solar irradiance. Okay. Similarly, the wind speed also varies. It is not constant, but you know that it depends. Like solar power depends upon the irradiance, and similarly, wind power depends upon the wind speed. Wind power depends upon wind speed, and solar power depends on irradiance and temperature. So it's not constant. What is the meaning of that? It's not constant. It's more volatile in nature, means they are variable. So always when there is a power is varying, okay, but the loads are also varying. So there is an energy storage device we have to bring into the picture. Okay. Then coming to the photovoltaics, if you see a typical IV characteristics, of course I am not dealing or detailing about the inner characteristics of the photovoltaic, but you know that the photovoltaics, if you see, like it is made up of simple p junction region, and usually there is a depletion region. Once if the photons fall on the depletion region, then electron hole separation takes place. Then the potential difference do exist. Then if there is an external circuit, then current flow to the external circuit. Then that's called electricity. Now, so for collecting that electrons and holes, there are some fingers, okay, on the PV, like you can see that like white color or even silver color kind of thing, which is basically to connect the current. Then if you see the typical ID characteristics, so this is so this is a typical ID characteristics. So what will happen was, what is the understanding from you, like out of this characteristics? Like here there are two characteristics. Have you seen the solar characteristics in case IV characteristics and power voltage characteristics? Some of your final years, those who are doing or at least starting, you might have seen that IV characteristics and PV characteristics. Okay. So can you tell me like what is the inference actually from this slide? Can anyone tell me what is the inference from this slide? Can anybody tell me what is the inference from this slide? So I have just plotted power versus voltage, and there are a couple of inferences. Like one is, you know that in case of solar, we talk about the irradiance. Like what is the irradiance of solar irradiation? So it depends upon irradiation. You can see. So one is 1000 watts per meter square, and another is 500 watts per meter square. Means we measure the solar irradiance in terms of watts per meter square. If you have more input energy, like more irradiance, then you get more power. Okay, that is what it was given. You can see the power value also in terms of kilowatts. You see, so when it is 1000 watts per meter square, this is one peak power at minus 25 degrees centigrade. Similarly, if the irradiance decreases to half, then power also closely reduces to half. Okay, you can see. But the important inference here is one is that is the irradiance changes, then the power changes. The other important inference is if the temperature is varying. For example, higher temperature you see lower power, and for lower temperature high power you see. So it depends upon both irradiance and temperature. And other important observation is you see that the peak power, wherever the peak power you see the peak power. So here there is a peak power, here there is a peak power. So I have just shaded, so you can see the shaded waveform here. This is the shaded waveform, you can see. The shaded region will tell us like the range of operation. So it is not a constant. It means at constant voltage you are not getting like always rated power. So different operating points are there for different irradiance and different temperature. The optimal operating points are varying basically. Is it clear? So that is about the photon. Similarly, if I take wind characteristics also, like they are also like not a linear curve. Okay? You see, for example, like the wind speed is 6 meters per second. Okay, if the turbine speed is another actually x-axis and the power output is a y-axis. So you can see here also at one turbine speed is here for a 6 meters per second you are getting optimal power. When the turbine speed is here you are getting 1.2, turbine speed of 1.2 you are getting optimal power. That means the wind speed changes, then the optimal turbine speed has to vary. You have to vary that. Okay, so that is one of the important difference from this slide. So coming to fuel cell, like this is also one of the promising technology. So unlike electric vehicles, and hydrogen vehicles also comes into picture. So where fuel cells are also part of it. So here what will happen was hydrogen is the input for the fuel cell, then we get the electricity. But you try to see the relation, you see actually what is its characteristics. So you can see here this is the current and this is a voltage. The current versus voltage, if you see, once if you draw the higher current, then the fuel cell voltage is dipping, it is decreasing. Okay, it is decreasing. This is about fuel cell. Now let us explore like why we need power electronics and what are the performance indices. Okay. You know that the wind energy can be in the form of AC or DC. Sometimes people are using PMSG, permanent magnet synchronous generators. Okay, sometimes people are using induction generators, sometimes people are using DC generators, permanent magnet DC generators. And similarly, for a solar, that the output is DC supply, and for like the fuel cell again DC supply. But our utility is again AC supply. So that power generation is at different voltage level sometimes, different frequency. But whatever we are consuming the power is a different mode actually. So it is AC supply. It has different frequency components. So they are actually different shape actually. We talk about wave shape. One is a constant DC. The difference between a DC. The difference between AC. Right? AC has a fundamental waveform. So we usually say that our required component is sin omega, like EM sin omega. But what we have is that sometimes we have DC supply. So there are lot of supply requires. Supply is giving one kind of voltage, but your load demands other kind of voltage. Okay. So then the power electronics comes into picture. It plays a major role. You know that there are a couple of converters like DC-DC converters. Why DC-DC converters? Why DC-DC converters? Last. DC-DC converter. I am here only your study. It's okay. Find here, please find here. Raise the hands who are finding and who has attended the faculty. Anyway, so DC-DC converters if you take, that DC means DC voltage, but sometimes the source voltage may not be constant because I have shown you right. In order to track the maximum power from the PV, the operating voltage is not always constant. It varies. Previous slide if you are looking for, it varies from 80 to 100 volts at the maximum power. Similarly, sometimes, like as I told you, the fuel cell, if I take as one of the input source, fuel cell voltage is also not constant. Similarly, if you take a lead acid battery or if you take a lithium battery, so their battery voltage depends upon their state of charge, SOC or depth of discharge. It depends upon SOC. So the voltage is also not constant. But sometimes, your mobile, some USB boards require 3.3 volts. Some headlights require 4 volts. So we require different voltages for different applications. But that voltage should be maintained constant. But the input is giving, but you need to maintain the constant voltage. So then you use a DC-DC converter. So you need to regulate the voltage. That's your target. The target application is to regulate the voltage. Sometimes you have a fixed input voltage. Okay, but I need to get different voltage. For example, I have 18 volts. I require some 3.2 volts. Then also we require DC-DC converters. Okay, what are the things? If the input voltage is varying, then we need to regulate the voltage. One is for DC voltage, one is for regulation of the voltage. But the regulation of the voltage as per our demand. We want 12 volts. Yes, you use the DC-DC converter. Okay, that is one of the DC-DC converters. Similarly, inverters like that even in your house appliances like also you use UPS, right? What are the apparatus of UPS? Have you ever opened what is there inside the UPS? Have you ever opened? I request, because being electrical engineers, like you please open some electrical apparatus. See, sometimes you go to the places where some air conditioner repair you go there, frequently go there. And then try to open, like they might be open, right? You see what is the inside components of air conditioners or whatever it may be, the electrical apparatus, the fridge or whatever. You try to open and then understand what is happening. Okay, that is the best way of learning. So fine. Now, if you see a simple UPS, like what we do is, that when there is a low power, then you usually get the power from the UPS. Right? That's what the UPS does. Uninterruptible power supply. What is that present in the UPS is like there is a converter setup, there are some batteries. Have you seen batteries? Batteries have you seen? Okay, battery stores energy in the form of chemical energy. So batteries are there, then we have a converter. Then what we do was we charge the battery when there is a power, but when there is no power, then we discharge the battery. That is what we generally do it. Now here, the battery demands DC supply, whereas our utility is AC supply. Then what we need, say converter is required, which converts from AC to DC and DC to AC. It is important because conversion is not possible because we cannot store the energy in AC form, but our utility is in AC form. So because we can store only in DC form, so AC to DC and then DC to AC is very important. So power conversion. So one application, one converter which I talked about is a DC converter. Other converter which I talked about is AC converter, and other converter which I talked about is DC converter. The other one is also there, but it is less prominent. AC converters. Basically, we don't study much. Even in your BTech 9 years and those who are participants, you might be knowing that our application of AC converters is very limited. Okay, but there are some applications, but they are limited applications. But you see DC converters, especially for PV and EV integration part, PV and EV part, photovoltaics and electrical aspect. The DC converters, AC converter, and DC converters plays a very important role. Power electronics plays a very important role. Then power conditioning. So another why power electronic systems is power conditioning. What is it by power conditioning? What is it by power conditioning? What is it by air conditioning? What is the purpose of air conditioning? Of course, to increase the comfort of human being. That's the whole purpose. How do you feel your comfort? So we always talk with respect to temperature. 25 degrees is a comfortable temperature. So air conditioning also does like it absorbs humidity also present in the air. That's why water is coming out, seen right. So both temperature and humidity plays an important role. So if there is a humidity in the air, then it sucks and then puts out. Okay. Now similarly, power conditioning is also very important tool actually. So you know that you require a AC waveform. You are electrical engineer, so you cannot say that I require a current, I require a voltage, not like that. So we require a fixed waveform with constant voltage. Sometimes what will happen was you might hear about SAG, when there are some power systems like especially in the quality of the power picture. To understand the quality of power, there are some words in terminology like blackout power, some terminology you need to understand. But the point here is using the power electronics, like in case if there is a dip in voltage, we can actually maintain the voltage constant. So which component is crucial to maintain the voltage constant, whether it is active or reactive components, to maintain the voltage constant. Anyway, so in order to supply, like we usually what in case if there is a drop in the voltage, we usually connect a capacitor battery. Have you electrical substations or near substations to your college? Please go there and then try to understand that there is a capacitor banks because most of the loads are inductive loads. So in order to we need to supply the reactive power before the capacitors are connected. So the same can be controlled loss. We can give whatever precisely I need some 6 kVA reactive power, then the power electronics is possible. Right? With the using power electronics, we can actually give the reactive power. At the end of the session, you should understand. Okay, we can understand if we listen properly. How can we control, like how can we actually give the reactive power as what we decide? Okay, and similar that is called power conditioning. So power conditioning is you try to give a reactive power when the grid demands reactive power. Okay, or you try to reduce the harmonics in case if the grid is drawing the harmonics. Harmonics, this is I mean, usually see when we talk about harmonics, we talk about the quality of the AC waveform. If the AC waveform has more harmonics, okay, then that is not good. We don't design it. What we want is EM sin omega t only. What is that we want? Give sin omega. But I don't want anything, any other waveform. But unfortunately, because of many noise devices, okay, we have some other frequency component also, like sin 3 omega t, sin 5 omega t, which is not desirable. I want only sin omega t. And another application of power electronics is influence matching. Maybe next when we talk about the converter, then I will brief about what is influence matching. Okay, then performance indices. This is also very important to you to understand. See, when there is a DC, the quality of the output waveform descends on ripples. Ripples is the one which we will talk about, like harmonics in case of AC, ripples DC. So always whenever we are designing any inverter or converter, we need to check the ripple content. Okay, the ripple content should be very small, harmonic content very small. Harmonics AC, ripples DC. Okay, DC means ripples, AC means harmonics. Okay, we need sin omega t. In case of DC, we need constant DC. We don't want a deviated DC. We want a constant DC. That is only these two are the high used signal for electrical engineers. Constant DC and other is DM sin omega. Okay. So one is input current, output voltage ripples, TSD. Of course, power factor is a part of TSD. What is the power factor? What is the power factor? Cosine of voltage, but it is not provided the waveform is sinusoidal. Provided if the voltage waveform is sinusoidal and current waveform is also sinusoidal, we can say that power factor is any between voltage. But power factor is a product of distortion factor and displacement factor. Displacement factor is a cosine of angle between voltage and current, whereas distortion factor is depends on the harmonic. I mean how near your waveform is near to sin omega. Okay, distortion factor is the waveform. For example, distortion factor is unity, there is no distortion. Is it clear? Power factor is given by distortion factor and displacement factor. Distortion factor is whether your waveform is distorted or not. It should be 1. So power factor is distortion factor and displacement factor. Try to understand. Okay? Then some of the other performance indices like one is efficiency, other is reliability, then the wear rating of course the wear rating of the devices, like cost and operational maintenance cost or operational costs are very important performance indices of a given power converters or power. Now, so let us start from the start. Like this is a semiconductor devices. You know that we have multiple classes of semiconductor devices, starting from diode. Have you seen diode? How many have you seen diode? Whether it could be IN4007 in case of analog circuits lab also you might be using diode. I think most of you have seen, though you are not right. I don't know why you are studying diode in the times. It's okay. You become bigger. Error is 18 plus. More into rise that. See, I think you might see the diode. Have you opened and broken the diode? Have you broken the capacitor? Have you seen the network? Please go to your lab maybe next. I request the faculty to please allow them to break the diode and the capacitors. Let me break it and see what is there inside. And then see, there are so many videos about how the capacitor is manufactured, how the inductor is manufactured, how the diodes are manufactured. See, unless you see the real components, you don't what to say. You cannot take the technology. Why the problem is, why the core companies are not coming? Is if they have to come here, they should take more people. See, in order to take more people, then they will see the fundamental understanding of what you are learning. So if you don't be in the shoe, then how do you we call as a electrical engineer. You are third year or fourth year or whatever it may be. You have to see the components. What are the real components? How they exist like that. Physical aspects are very important. Power electronics you are studying, you are talking about transistors, you are talking about SCR, so many devices we are talking about. You have to see this. Please at least watch videos about the physical, how they are physically available. There are so many packages like 227, 247, some packages are there. Okay, anyway, coming to the slide, today we have a semiconductor device. You know that these uncontrolled devices. What are the uncontrolled devices? We know theory, like we know X-ray, but we have to do practical also. We have to check the diode practically how it is. Diode is basically an uncontrolled device. It will flow like the diode starts conducting once if it is forward bias. If it is reverse bias, it is like a turn off. Turn off. It will be turned off, right? Then that's what uncontrolled. Uncontrolled means there is no control in our hand. The circuit becomes forward bias, the diode conducts. If it is reverse bias, diode will turn off. Then the other kind other class of switches are semi-controlled devices. So semi-controlled devices means thyristor, triac, they come into the family. Semi-controlled switches. That means turn on is in our hands. Like turn on is in our hands. Like for example, just imagine that I have a simple sine waveform. I want to start at pi by 2. Pi by 2 means at omega is equal to pi by 2. At that time I want to start. Then I sense where is the 0 point. Then after some pi by 2 I give a signal to SCR. Then SCR will turn on. Okay, SCR will turn on. But to turn off the SCR there is nothing in our hands. So the circuit current has to come to close to 0 or less than holding current. Then only it will stop. So in case of diode, there is no control. If it is forward bias, it will connect. If it is reverse bias, it will stop. But in case of SCR, we can turn off at what the instant we want to turn off. But turn off depends on what? The holding current. The current should be less than the holding current. It depends on the circuit actually. Then IGBT or MOSFET, it's a fully controlled device. So what is that it says? Like if if we give a pulse, it is turned on. If you remove the pulse, it is turned on. What is between turn on and turn off? Turn off. No, one is to make the break. For example, like you can realize that okay, you can realize like the turn on means you can realize like a switch. Is it clear? Turn on, you can relate like a normal switch. You are turning on fan. Simple, like instead of you turning on, a semiconductor switch actually playing a role here. So now once they invented the semiconductor device, we see so many converters as coming. DC-DC converters, DC-AC converters, AC-DC, then AC-AC. You see so many converters are there. So one is if I categorize the converters whole, there are one broad classification is isolated converters, non-isolated converters. What are they? Isolated and non-isolated. If I broadly classify the power converters, there are two types of converters. One is isolated converters, other is non-isolated converters. One is soft switching converters, other is hard switching converters. Okay? One is soft switching converters, other is hard switching converters. Okay, and the remaining converters, like again, this is a broad classification. Out of that, we have like push pull converter, it is isolated, full bridge, flyband. So many are there. So many people are developing new converters also. Okay. So let us come to the actual area, like we are targeting today, our session is targeting about power electronics related to EV and power electronics related to EV. Okay. So, as I told you, like we have like PN material and the right forms, then electron and hole separation takes place. Then if some electrical circuit is connected, the current will flow. So there are two types of technology, widely used technology. One is polycrystalline, other is monocrystalline. So this is simple mathematics. So no discussion here. But the important point is if there is a, like if you simply take a PV pattern physically, then you can take voltmeter, then you can parameter. Then if you vary the resistance, and then measure voltage and current. Then you are plotting, actually you are measuring V and you are measuring I for different values of resistance. If you take V and I, then you calculate power is what is the formula for power in DC? V I know, I know. What is the power? What is the power? Some hours. Voltage is there, current is there. How to find power? VA. Simple VA. So then we find VA. But if you plot power versus voltage and current versus voltage, so this is current versus voltage. This is the current and this is the voltage. Okay. This is for single panel. This is for single panel. You get current versus voltage like this. Okay. But if we connect in series two solar panels in series, then what will happen if I connect two solar panels in series? Voltage will double, right? No, you get this kind of, like this is how you get that. This is a new current. But if I connect them in parallel is current will be added, current adding. So this is a new idea because they are parallel. Like this kind of panel, single panel, this is single panel. But if I have two panels in parallel, then current will be added. Okay? So finally you get this type of curve once they are connected in parallel. This type of curve when they are connected in series. Means current will be adding if they are connected in parallel and voltage will be adding when the panels are connected in series. Okay, this is these are some specifications. Like, with this I have shown you what to say IV characteristics. So if I take any panel, like in the market, whatever the panel, have you seen your solar system 200 kilowatt? Have you gone through your solar plant yet? Huh? Some of it is fun. You might have gone through it. Okay? You go to panel and then see, try to see what is the back side of the panel. They give a specification. Solar panel has some specifications like one is open circuit voltage, short circuit current, voltage at maximum power, and current at maximum power. Okay, these are some parameters. Okay? Peak power. Peak power. Some specifications. You try to go to the panel and then try to find the data sheet. Or at least today you do that. The solar panel you take Vikram Renewable 300 or whatever the models you available. Just try take 300 watt solar panel and then try to download some data sheet and then see what is there inside the data sheet. Okay, these are some important parameters, but there are some other parameters also like temperature coefficient, current, and voltage temperature coefficient. So this is again I have drawn in the same specifications I have taken, and then I have taken like 6 panels in series. Okay, and then you know that when they are connected in series, then voltage is leading. So this is a voltage and this is a power. So previously it is 20 watt panel. If all of the 6 panels are connected in series, you are getting 120 watts. Okay. But here I kept some parameters. You should notice some parameters. One is lambda, usually is irradiance in terms of kilowatts per meter square. One is 1000 watts per meter square. And then other is IPP and DPP, means current from the solar panel is terminology here I use as IPP, and the voltage of the solar panel is DPP. Okay. Then why we need NPPT? Because as I told you, like if you see a simple DC source, if I say this 6 volts, that 6 volts is constant mostly. Or it may vary, very other way also. It may be 1 ampere or 2 ampere, 3 ampere. But here it is a different case. You see here the solar is neither a constant current source nor a voltage source. You can see here it behaves like a constant current source. Here it behaves like a constant voltage source. You see here. It's neither a current source or a voltage source. So the point is, you can see here it varies. That is, when we are drawing different currents, the voltage is not constant. Okay. So and moreover, we need to see. For example, I kept some 1 kilowatt panel. Then my intention is you try to grab whatever the power is available and then try to give it to grid or your house appliances. Okay, because to reduce the energy consumption, or the important aspect is you already kept a lot of money for purchasing the solar cell. So whatever is available, you try to absorb the power. For example, the PV can give 100 watts at particular range, you try to get 100 watts. Or if it is giving 200 watts, you try to get 200 watts. Okay. So it depends upon, as I told you, it depends upon irradiance. Based on the irradiance, some power is available, you have to absorb the power. Whatever the power is available, you have to absorb the power. So imagine that this is, I am talking about temperature 45 degrees. So that means this is a PV curve. So what is the best place, best operating point is you have to operate here, somewhere there. Somewhere this is an operating point. If you operate here, you are getting maximum power. Okay. Other points are not optimal points. So this is your operating point. This is your operating point. Okay. This try to understand. The operating point should be varied for maximum power. The operating voltage is not a fixed value. It should be varied for getting an optimal power or maximum power. Then partial shaded conditions is one of the other issues in case of solar. Sometimes what will happen was because of if you don't install it improperly, if you install it improperly, or if there is because of neighboring trees or neighboring buildings, there is a probability that solar cell may receive a non-uniform irradiation. That means all the panels will not receive equal irradiance. That is the partial shaded condition. Are you getting the point? All the panels will not receive uniform irradiation. They are actually, some panels will receive 1000 watts per meter square, some panels will receive 60 watts per meter square or 600 watts per meter square. Okay, because sometimes these clouds also plays an important role. Okay, clouds plays an important role. What will happen with the partial shaded conditions is, see, this is one diagram I have shown you. This is the agro photovoltaics. This is the terminology is agrovoltaics. So what usually they do was, in case of agrovoltaics, same land we use for both PV and agriculture, both aspects. In the conditions, the tilt usually we maintain constant. We usually maintain constant tilt, like for the given location to get the maximum energy. Like there are, like for a given location, there is a constant tilt time. We have a constant time. I think even if somebody watches your solar park also in 200 kilowatt plants, then they tilted in one direction. So it depends upon where you are actually. Depends upon your location. You can understand which is the best tilt angle. But this when we talk about agrovoltaics, it is not only that there are two objectives in case of agrovoltaics. Not that only getting maximum power in the solar, but there is another important aspect also. You have to see that higher crop yield also. Further, the shading angle, this position plays an important role. Okay. So when we have different positions, what will happen was, again here we experience a partial shaded condition. Okay. So partial shaded conditions because of neighboring trees, neighboring buildings, because of clouds, and other is tilt angle. Other is tilt angle. That is also plays an important role. So what will happen? What is the resultant of the partial shaded condition? Is this kind of curve. This is the power source. Previously, if there is no partial shaded conditions, the previous is like this. Okay, the previous power is like this. Actually, I have shown previously. But once if you have a partial shaded conditions, you see the waveforms will change like this. So here you should understand one terminology called local maximum power point and global maximum power point. So once again, this point, so if we have a single point, people have not differentiated. They say MPPT only, MPPT maximum power point packet. So this is a place, single peak. But if the panels experience power shaded conditions or tilted, then what will happen is you have multiple peaks. Okay? Multiple peaks. What is the local peaks? What is the global peak? I will put ABC. We will tell you what is the local peak and what is the global peak. Okay? A, B, C. And here I will put like small a. What is a local peak? What is a global peak? In first wave, what is the difference from the slide is, you know that after partial shaded conditions you have multiple peaks. One among them is called global peak and the rest are called local peaks. Here B is giving more power, so it is a global peak. And both A and C are called local peaks. What about the other way? Small d is maximum power, so small d is called global maximum power or GMPP. We say GMPP, global maximum power point, and other points are local points. So this is one inference. Okay. Anybody can get anything out of this IV characteristics and power versus voltage? You see that this B is maximum at something close to 50. And whereas D comes at 100 volts. So the maximum power point operating point is very important. Where why power electrons comes into picture is you will change the operating point to desired value. The power electrons, that is what impedance matching does. I will show you later. With respect to power electrons, what you can actually do, you can bring the system to operate here. You can bring the systems to operate where we actually want. That is the purpose of the power electrons. We will see what. So this is a model. Of course, I don't want to detail you because one aspect is, especially for modeling the partial shading conditions, we talk about the voltage aspect. So with respect to the voltage depends upon the photocurrents of the individual panel. Okay. This is again some IV curves and PV curves I want to show. This is a standard curve and this is the partial shading conditions. The corresponding IV curves. So this is IV curve for normal uniform variance and this is a IV curve for partial shading. Now, what is this line? This is I and this is B. What is this line? What is the slope of that line otherwise? What is the slope of that line? What is slope? How to find slope? For a given rate, I have a bottom here. How to find a slope here? Now you tell me how to find slope. This point. What is that? How do you find slope? Delta y by delta x. Is it slope? You will be doing right. Slope is equal to y2 minus y by x2 minus x1. You know, right? So this is one slope actually. But here is delta x, delta y by delta x. So delta I means here you get I by b. Correct? I by b is nothing but what is I by b? What is the reciprocal to resistance? Conductance. G. We usually denote G, right? Resistance reciprocal is conductance. Okay. G we denote. R is the resistance. B by I is the resistance. I by B is the conductance. Okay. So there is a basically a resistance is playing important role. So for example, like here, like all of us see here, please all of you have a. I will put like this. let this is 100 and this is something, what is this, Asian maybe 80 for example. So what is 100 by 80? So B is 100 and this is 80. And for our calculation I am assuming this 20 instead of 80 I am assuming 20. Then 100 by 100 by 20 is 5. So what will happen was if 5 ohms is connected, you are actually operating somewhere here. Okay. If 5 ohms is connected, you are operating somewhere here. So I will take another point. So this is 5 ohms here. So if I take here, what will happen was this is 400 and the current I can assume is 6. So or I will take 5 here also I will take 5 just for our convenience. So 400 by 5. What is 400 by 5? It is how much? How much watt is 400 by 5? 80. Correct? 80. So it is 80. So if the resistance 5 ohms is connected, just imagine I have a solar panel. If 5 ohms is connected, I will be the operating point is here. The voltage is 100 and the current is somewhere here. If I change the resistance or if I increase the resistance, what will happen was, so it operates sometimes here, it operates sometimes here. So this will vary. The operating point will vary. So you adjust the resistance across the panel so that you are here. Okay, ultimately what you are supposed to do was adjust the resistance across the PV and then try to operate at maximum power. That is called MPPT. Okay, try to vary the resistance across the solar panel and then see that you are tracking the maximum power. You are getting the maximum power. That is called maximum power. Okay, now we will see the conventional PV system. How the conventional PV system is there. So we have a DC link or sometimes a fixed resistance load, and we have a DC-DC converter. Then we have a PV. Then we have a MPPT converter. If you open your physical system also, then you can see this kind of parts. One is PV panels, then some DC-DC converters, then DC link, then MPPT converter. Okay, MPPT controller means, so basically there are two types of MPPT. One is called tracker, other is called algorithm. Okay, one is called tracker. DC-DC converters is called tracker. It is like this actuator. You know actuator. Actuator means, for example, I want to lift this pen. I am lifting. So here there are two things are happening. One is we are lifting the pen, but who gave the instructions to lift the pen? Mind, right? Similarly, there is a mind, there is a system, there is an actuator. So here the mind is MPPT controller. So another page where we write the code in microcontroller, or sometimes even using analog circuits also it is possible. And the actuator is a DC-DC converter. Who does is a DC-DC converter, like a muzzle. Okay, now let me come to the important aspects of how to change the impedance for PV. This is very cool. basics. I think you appreciate this. So the buck converter and the boost converter, buck boost converter, these are some DC converters. What is actually happening was, this is a simple representation I am showing you, like input voltage. This is input voltage. So this is input voltage. Then we have a load here. So plus minus V naught is your load. What is your actually in case of a DC converter? It is a buck converter. Buck converter means I need to reduce the voltage. That's my application. I think you have studied about step down transformer, step up transformer, right? Similarly, in case of DC converter also, it is possible to convert one level to other form. Okay, so we can increase the voltage or we can decrease the voltage. But so here what we are talking about is a buck converter. Buck converter, what it does? It reduces the voltage. So you have some input voltage. You have 100 volts, for example. You want to reduce to 50, you can reduce it. If you want to reduce to 4 volts, you can do it. Now, so what actually we are doing was, like this is point A and this point B. If the switch is connected A, then output voltage is equal to input voltage. If the switch is connected to B, the output voltage is equal to how much? If the switch is connected to B, what is the output voltage? Plus V naught is here. V naught, I am talking about V naught. V naught is equal to B if it is in A. If it is in B, what is V naught? If it is in B, what is V naught? How much? 0. So it is like this. So I am plotting this is with respect to time, and this is V naught. Okay, during like once the switch is on, so like this V naught is green, that is green, and the switch is off, V naught is 0. Okay, this is the waveform you get, like on, this is on time, this on time is given by T on, okay, off time is given by T off. The total time period is T. Okay. Now, if you see this waveform, if I want to get lower value, then what I should do? Average value. What is the average value? How to find average value? DC component is basically an average value. 1 by T, 0 to T, then will 0 to K component. So more on time will have more voltage, less off time will have less voltage. Correct? You know that V naught is equal to, what is the formula? V naught is equal to, if I want to find average value, from this waveform, 1 by T, 0 to. So this time I can take like dt or T on. So I can take like dt. Then so dt. So because V naught is equal to V at that time, what I wanted to convey was, if you have more on time, so you get more voltage. If you have more off time, you have less voltage. That's a simple straightforward thing. Now, this waveform, just imagine that if it is 10 volts, I want to get 5 volts, then off time should be equal to on time. If I do that, then average value I will get what? I will get average value, how much? 5 volts I can get. But what is my expected voltage? Is a 5 volts. But I want a DC voltage. But here this waveform has 10. If the switch is closed, you have 10 volts. The switch is open, you have 0 volts. So 10, 0, 10, 0, 10, 0. But what I want? A constant 5 volts. I don't want 10, 0, 10, 0. I want a constant DC. Okay. Then if this is a constant, whatever I want is a constant, but I have V and V. So this is called ripple actually. This is called ripple. What is it? This is called ripple. I don't want a ripple actually. I want the output should be a 5 volts. It should be a constant. But what we are getting from this is 10 volts and 0 volts, 10 volts and 0 volts. So this waveform has two components. One is DC component and another is AC component. If you dissect the waveform using Fourier series, there are two components are available. One is DC component, other is AC component. Now you tell me, my load demands only DC component. I don't want AC component. I want only DC component. I have, of course, the waveform has the input. Here I have both AC and DC, but I want only DC component. Then what will you do? you want only DC component, then what we will use a low pass filter. What is low pass filter? What is low pass filter? Inductor and capacitor. Okay, we take inductor and capacitor. So this is how we take it. So the inductor and capacitor. Now to realize the actual circuit, I think you might study it also in your PE course. Okay, this is basically a buck. Okay, this is basically buck converter. So what buck converter actually does is we cannot actually switch. You see, we cannot basically switch. And if we control the switch all time, we can vary the voltage like what we described previously. But here we have both DC and AC component. But what I want was only DC component. I want that. Then, if we connect the NRI in series, what is the impedance offered by the L when it is in series? What is the impedance for the inductor? No, LDA is a voltage. I am talking about the impedance offered by the inductors. Z. Omega L, right? Impedance offered by the inductors is omega L. Impedance offered by the capacitors is 1 by omega C. So the impedance offered by the inductors is omega L. The impedance offered by the capacitors is 1 by omega C. How they are connected? One is connected in series. So here you see, one is connected. I'll show the same slide here. One is omega here, other is 1 by omega C. One is connected in series, other is connected in parallel. One is connected series to the road, other is connected parallel to the road. Okay? But L is connected in series, so it is omega L. So for high frequency component, the impedance is very high. What is the impedance high? It allows low current. So for high frequency component, it allows low current. Similarly, there is a capacitance. Capacitance connected in parallel. What is the impedance offered by the capacitance? It is 1 by omega C. For high frequency, what is the impedance offered by the capacitance? 1 by omega C. Whether it is high or low. For high frequency means omega is high. 1 by omega C means omega is the denominator. So if omega is high, then impedance is low. So that means the inductor is basically opposing the omega component, high frequency component, whereas capacitance is allowing the high frequency component. Okay? So the inductor here is acting like a blocking, actually it is blocking the high frequency component. The capacitor is bypassing the high frequency component. It is allowing. It is allowing means it is passing through the capacitance. So what is the resultant waveform here we will get? One is stopping the high frequency component, other is bypassing. So it is allowing, it is seeing that even if some high frequency components are available at this point, this capacitor is bypassing that. So ultimately you are getting a DC waveform which has low frequency, low high frequency component, low high frequency component. Are you getting the point? Once again, see in previously what we have seen was in the previous slide. We have DC and 0, but what we want a constant voltage. But the average voltage is the DC component. Okay, so the DC component, it is for the impedance offered by the DC component here is 0. The impedance offered by this is infinity. Whatever the DC component is there, it directly comes to the DC, to the load. The DC component is directly coming. But for the AC component, Z is offering, Z is more. And here Z is very small for the AC component. So this is basically blocked and capacitance is bypassing. Therefore, only you are getting a DC component. Is it clear? Once again, so we have both DC and AC component. And we have 10 0 10 0 or 100 0 100 0. But if you use L and C, L blocks high frequency component and C, which is connected parallel to the load, bypasses high frequency component. The resultant is a DC component. Okay, you get a very close DC value, like very close DC value is almost constant, like 5 volts. Is it clear? Now, of course, there are some what to say, on-state equations, off-state equations, and then some ID characteristics. But these formulas are very important, especially for designing as well as deriving the EEE equations. One is the voltage across the inductance over a period equal to 0, the steady state condition. Similarly, current to the capacitance must be equal to 0 in the current under steady state condition. That is a current EEE equation, other is voltage gain equation. So we can derive based on volt second balance of the inductor and amp second balance of the capacitor. Of course, I don't want to go in deep about the design aspects also. Now coming to boost converter. Okay. So previously we discussed about a buck converter. What is the boost converter? First of the voltage. One minute, I take one. You know that in a transformer, like how we reduce the voltage, we can also increase the voltage. You know that, right? Which parameter will influence the transformer voltage? Transformer voltage. In a transformer, if you want to increase the voltage or decrease the voltage, which parameter will influence? Just take a positive zone. First step of N1, N2, number of turns in primary winding, number of turns in secondary winding. You tell me now, you tell me, how do you get more voltage? How do you get more voltage? If N3 is greater than we get more voltage. N3 is greater than we get more voltage. So here, in case of a boost converter, here also like we need to increase the voltage, but here there is no transformer. There is no transformer here. Okay. But what are the different aspects in case of a transformer? So we assume that V1 I1 is equal to V2. This is one aspect. Okay. Correct? You know this relation? V1 I1 is equal to V2. We assume that the transformer is lossless. We can say that V1 I1 is equal to V2 I1. Similarly, if you take any DC-DC converter, so if you take DC-DC converter, here also we assume that this condition is satisfied and then we go for analysis. Okay. Now, what are the different elements in case of a DC-DC converter? One is inductor, okay, L, and other is the capacitor, other is the switch, other is the diode. Okay. So if you take a simple switch, okay, ideal switch otherwise. So what will happen was the current is equal to 0 if it is open circuit. If it is a closed circuit, the voltage is equal to 0. What is the total power? What is the total power? I mean the absorbed by the switch. When the switch is open, the current is 0. When the switch is closed, the voltage is 0. The total power is how much? 0. So all the components in the converter, DC converter, actually absorb 0 power, ideally. So then if we assume that the converter is lossless, like a transformer is lossless, then we can assume that this V1 I1 is equal to V2 I1. Okay? We can assume V1 I1 is equal to how much? V2 I1. So I put some numbers here. 10 into 10 is equal to, so this can be 100 into 1 or it can be 1 into 100. I mean, I have put into two things. One is like 10 into 10 is equal to, that is V and this I and this V into I. So if I want to, so this is like 100 buckets, 1 into 100. Okay. There are two aspects here. We have discussed about the buck converter. But for a boost converter, what we actually do was, so that is we reduce the current to increase the voltage. Actually we do was we reduce the current to increase the voltage. Boost operation, how we are able to do? It's basically current buck operation. We are bucking the current to boost the voltage. Okay, once again, for assuming that the converter is a lossless converter, V1 is equal to V2 okay, V1 is equal to V2 to increase the voltage, we are basically reduce the current. That is basically a boost. Okay, now you tell me, in practical, how do you reduce, is there the current source, or if there is a voltage source, how do you convert it into current source? How do you convert it into current source? You have to take a large value of inductance so that we can actually, large value of inductance if we take, then we can actually convert a voltage source into current source. Okay, that we will discuss later. But imagine that I have a current source now. Now I have a current source, IE, and this is I0. Here is IE, and this is I0. What happens if the switch is, I have taken here A and B here. What happens if the switch is at A? The switch is at A, what happens to the I0? I0, how much? When the switch is at A, I0 is how much? You see the circuit, tell me. This is I0 and this is IE. What happens to the switch? What happens to the I0 if the switch is at A position? If this is here, what happens? I0 is equal to, if some response is there, then I feel more comfortable. Anyway, it's okay. So this is I0 and I0 waveform is like this. If the switch is at B position, what will happen? What is I0? By the current flow to the lowest part of the resistance. When the switch is at B, the current flows like this. Okay? This is the path of the current. Okay? So I0 is 0. But if the switch is A, the current flows like this. Okay? So the waveform is, when this is at A, you are getting I0. When this is at here, it is, you are getting 0. So like this, you are happy like this. Okay? So if this is I0 and if this is 0, the average current I can vary. Average current I can vary, right? Based on like whether it is more on A, then I get more I get more current I get, otherwise less current I get. The same, whatever the principle we talked about, the backing of the same thing. Switch off. Whatever the current, see, we discussed about the buck converter with respect to voltage, right? The same thing we are discussing with respect to current in case of boost and so on. So odd time is there, off time is there. If you want to reduce the current, then we just change the, so time will actually, if it is at more at A, then we can actually reduce more. Okay? Is it clear? So with this element, what actually we are doing was, I0 is can be varied from 0 to again I can vary based on the odd time and off time. So if the switch is here, if it is continuously here, I0 is equal to IE. This is continuously at this position, I0 is equal to how much? 0. So if I change the I0 between A and B, I can actually vary the average at I0 I can vary. Okay? The average I0 I can vary. Once if I change the average I0, that itself indicates if there is a lossless, the current is reducing, that means we are actually boosting the voltage. Is it clear? So if you take a practical voltage source, to bring the practical voltage source into current source, we will connect a large value of here, this one. This 2 becomes like a current source. This is equal to this. A voltage source, large value of inductance, they are connected in series, it becomes like a current source. Then to increase the voltage, we have to buck the current. So who does that bucking the current is a parallel switch does it. Okay? So we use a parallel switch. You see here, we use a parallel switch here. So once if you use a parallel switch, this is a load current. Okay, the load current we can change the load current based on how much time. If the switch is completely turned on, output current will get very small. If the switch is completely open circuit, we will get IN is equal to I naught. IN is equal to I naught. So like this, actually what we can do is we can vary the I naught so that we can vary the output voltage. Okay, we are basically bucking the current. The load current we are bucking. How we are bucking? The source we are making into current source. Then we are making a parallel switch. If the parallel switch is there, then load, if the parallel switch is closed, the load doesn't experience any current. Because the current flows through the lowest part of the resistance. So at that time I know is 0. Like the PA, and I able to change the average current. If I able to change the average current, then the average voltage is changed. We can increase the voltage by satisfying the relation V1 I is equal to V2. If I buck the current, the voltage is boosted. Okay, this is a principle of boost operation. Boost voltage, current buck. Basically, it is a current buck, which is nothing but voltage boost. Okay, clear? So this is one aspect. And one more important point is here also we experience some ripples, delta I, which you don't deserve. You don't want like I want like a constant voltage. I want a constant voltage. Okay, so but here we have like it has some waveform which I don't require. I want only constant. Then we need to use LC filter. Of course, already inductor is there. Already inductor is there. Therefore, other component is capacitor. You have to connect a capacitor. You have to connect a capacitor. But here why diode? Because capacitor is a voltage equivalent. You know that is a voltage equivalent. Capacitor and the switch should not be connected in parallel. Is it clear? Capacitor is a voltage equivalent. You should not connect both in parallel. So you need to allow the capacitor to charge, but you should not allow the capacitor to short circuit. Then this diode is basically here. Okay, this is a simple boost current. Okay, stop here and take it. Come to the next one.
Start. Sir? 12:30, sir.
Yeah, so we have seen this boost current, right? So basically boost current is a current buck current. But existing voltage source we convert it into current source, then we will buck the current, then your output voltage experience higher. That's a working. Then coming to the steady state waveforms, like basically once the switch is on, the switch is off. So if you do it, then we will get the steady state waveform. For example, the switch is on. What is EN? EN is equal to, like if you apply KVL for this loop, EN is equal to EN. Then IC, if the switch is on, actually diode is off. Then IC is equal to minus A0. And similar current is off state. If you apply KVL for this loop, then you get EN is equal to EN minus A0. So if you apply KCL at this node, you will get this equation. So here, you know that for deriving the gain equation, especially for the derived gain equation, the average voltage must be equal to 0. Or even from the capacitor also we can derive the gain, that is average current to the capacitor equal to 0. So you know that this is a VP time. So this EN is equal to V and this EN is equal to V minus V1. So applying the voltage second balance, what will happen was we will get a gain is equal to 1 by 1 minus V. Okay, this is a 1 by 1 minus V means the output voltage V0 by V is equal to 1 by 1 minus V. So if just imagine that V is equal to 0.5, what will happen if it is V is equal to 0.5? It is 1 by 1 minus 0.5, it is 1 by 0.5. 1 by 0.5 is how much? 1 by 0.5. It's a 2. That means if you want to increase the voltage with a gain of 2, then we should operate this converter at a degree ratio of 0.5. Okay, if we change the duty ratio, then we can change the output voltage also, because the output voltage by input voltage is given by 1 by 1. So these are some characteristics, I mean some steady state waveforms. Okay, but so very important steady state waveform is a IL or input current. You can see this figure. You can see this figure again. Okay, we know that in case of the delta I is equal to V into dA by dt. We know one relation is equal to L into dA. L into dA. Or delta I is equal to, so VL by L dt. So otherwise delta T can put in terms of delta T. So delta I is equal to VL by L dt. So during odd time, you see voltage is positive. Voltage across net is positive. Therefore delta T for a given time delta T, then VL is positive means delta I is positive. Delta is positive means it is. But during off time V minus V naught, if it is a boost converter, V naught is higher than input voltage, so VL becomes negative. If it becomes negative, then delta I is negative. So delta I comes like delta is negative like this. So this is a IL waveform. Whatever I am talking is this one, IL waveform. Okay. Now, so buck boost operation, basically how this we are doing was, we are actually taking for the electrons from the buck boost. We can actually derive the buck boost. So buck boost. Okay. So this is a buck converter. This is a boost converter. So you know that in case of a buck converter, like the switch is in series, so we use this switch to regulate the voltage. Once if we are able to regulate the voltage, then we can actually decrease the voltage here. Here we are able to connect in series with some inductor, so that becomes current, then we are working the current to get the higher voltage. This is a buck boost converter. Okay, so we will see what actually why it is a buck boost converter. Okay, so here just imagine that if here if the switch is at here, what is here? What is here? When the switch is at here, what is here? Here is equal to VDC. And at here, finding it at A. So the switch is at B. I put like this minus plus. Means I put minus plus. Once if I put the voltage like this, once the switch is at B, what is VL? VL is equal to how much? Minus 1. Okay, so if I take like this, one is VDC here, other is V naught here. Minus means I remove the polarity because I have kept in the negative. Okay. Now always remember, under steady state, the average voltage across inductor must be equal to 0. That means the positive area must be equal to negative area. The positive area must be equal to negative area. Okay. This area must be equal to this area. So just imagine that if I decrease the voltage, so just imagine that if I decrease the, okay, I decrease the odd time, for example. So odd time means VDC. So during the off time, so this is just imagine that this is odd time, and till this time is off time, for example. Then this area has to be equal to negative area, then this width should be very small. Okay, then this area can be equal to this area. That means duty ratio actually deciding the V naught magnetic frequency. Similarly, imagine that this is odd time is very high, means DT time is very high. DT time is very high, then we know that VL is equal to VDC. So this is VL is equal to VDC. But during off time, so to satisfy this area and this V naught has to be very high. Okay. So here what we are finally we are concluding is, depends upon on time to make the area positive area equal to negative area, the V naught will modify. So at one place here you see V naught is less than V, especially when the duty ratio is less than 0.5. So here is the duty ratio is equal to 0.5, where on time is equal to off time, this period and off. This time is equal to this time. So if this has to satisfy that this Bn and B0 should be equal to Bn. Whereas there are some times that duration might be higher. So once the duration is higher, off-time is very small. Then if this area has to be in this area, then this negative peak should be very high. Correct? To satisfy the voltage second balance, the average voltage across must be equal to 0. So sometimes we have more on time. Within small time, off-time is very small. Within small time, you need to see that this positive area should be equal to negative area. That means the V0 is higher. Okay. For a lower on time, then you know that this area should be, we need to maintain equal to the negative area. Then the V0 magnitude should be very small. That means the duty ratio is a parameter. If I vary the duty ratio, then what will happen was, so we will get a relation like d by 1 minus. This is the relation of the buck boost d by 1 minus. Anyway, so here what we are doing was, we can actually buck the voltage, we can boost the voltage. That is why the name is terminology is given as buck boost. Then some steady state waveforms here we have shown. So whenever it comes to steady state, we have to see that what is the inductor voltage, what is the capacitor current when it is on, what is the inductor voltage and capacitor current when it is off. So here, if you apply KVL, the switch is on, here is equal to VA, which is equal to and then IC is equal to minus I0. When the switch is off, here is equal to minus I0 and IC is equal to ID minus I0. Okay. From this, if you apply average voltage, see here you see average voltage equation. That means during on time, the voltage is Vn, the time is dt. Okay. So voltage is Vn, the time is dt. During off time, Vn is minus V0 and the time is 1 minus dt. dt means on time, dt, duty ratio. dt means on time, 1 minus d into t means off time. So if you do that, then if you bring a Vn by V0, then we get V0 by Vn is equal to d by 1 minus t. Okay. d by 1 minus. So if I change the d value, then I can change the output voltage. The d is less than 0.5, it is 0.5 by, sorry, 0.5 by 1 minus 0.5, how much? It is 1. If you take 0.6 divided by 1 minus 0, minus 0.5, it's 0.6 by 0.4. The denominator is greater than numerator, so it is always greater than 1. If you take 0.4 by 1 minus 0.5, that is 0.4 by 0.6. Numerator, sorry, denominator, numerator is less than, okay, 0.4 by 0.6, denominator is more, so it is buck, okay, buck operation. So on the other hand, the d is greater than 0.5, it is boost operation. Is it clear? That is how a simple buck boost converter has come. Okay, actually what we are doing was, we are using some inductor basically, and then we are basically switching between 2 points to see whether to boost the voltage or whether to buck the voltage. Now let us come to a very important point. Why we are discussing when we are talking about the PEs for impedance matching. Okay. So I put a simple aspects here. Just imagine that this is a P. This is a P. Okay. Just imagine that this is a P. And I already briefed you before, like this resistance has to be varied and should be operated at RMPP where we can get the maximum power. Okay. So this is we need to actually bring it to the RMPP so that we can find the maximum power. Now we know that there is a relation like V1 I1 is equal to V2 I2. You know this, right? Similarly, I can put in terms of input and output. So this becomes V in is equal to V0 I0. In case of buck converter, first I put the power V0 I0 can be written as V0 square by R also, right? So it is a resistor load. The power V0 I0 can be put as V0 square by R. Now this becomes again I take V9 is equal to V0 square by R. Okay, but what is V0 in case of buck converter? V0 is equal to D into V. In case of boost converter, V0 is equal to 1 minus D is 1. V by 1 minus D. But I am taking, for example, I am taking a buck converter. Then V0 is equal to D into V. If I substitute V0 is equal to D into V, then we get like this. V is equal to D square by R. Okay, this E and then square cancel, then I am bringing I in the other side. then what will happen? Dn by dn is equal to r by correct? I am bringing the other side and r by d square will come. That means what I want you to understand was, see, though you are taking fixed rho, but if you change the d value, then I can change v1 by n. What is v1 by 1? v1 by 1 is the impedance output across the solar. So previously I told you, if I change the r value from 0 to infinity, some place you will get the maximum power. Some resistance you should get the maximum power. So now is that how do you vary? Like one aspect is you take your rheostat and vary, and then you try to see that you try to get the maximum power. But who will see there is some sun is there, like you are getting some variance. Then will you do physically and then vary the rheostat and then see, okay, at this resistance you get the maximum power. You cannot do it, right? You cannot see, sometimes irradiation changes, then again you have to vary. So physically it is not possible. Then what you can do was, you adjust you take a DC converter. If you adjust the DC converter, the resistance across the solar panel will change. Okay? The resistance across the solar panel will change. Now, somebody has to replace our eyes. Okay? Because we know that like once you change the resistance, or see whatever we are doing mechanically, we should replace it automatically. So previously what we do? Previously what we do was, you can see here there is a TV. I told you that, like if you take a rheostat, if you vary rheostat, what we can do was, imagine that this is a power and this is the ID term. If I change this R value, resistance value, the operating point will change. So I need to keep this operating point so that I get the maximum power. Okay, this is what how I can do was, I can connect a simple ammeter and then voltmeter and then I vary the ammeter and voltmeter and see where I get the maximum. I stop the resistance where I get the maximum power. Okay, now you have to replace it. Actually, this is what we are doing. We are actually doing it physically. So you have taken your rheostat and then varying the resistance value and then measuring the voltage and current, and then you are seeing where you are actually getting the maximum power. But now you are actually you have to replace it with a automatic. Like your actuator is basically your muscle, like right? The rheostat actually we are varying, but our eyes are like the sensors. We are measuring voltage and current. And brain is the algorithm which actually thinks that here we have more PA compared to previous PA. Like that we will identify where the maximum power is. Okay. Now the same aspect we replace with a power electronics aspect. Okay. How is like this? We have a PV. Okay. We have a DC converter, and we have a resistance, fixed resistance. Okay. Now all of you see here, just imagine that I operated with one duty ratio. Okay, some duty ratio I operated. Then here we have one equivalent resistance. Okay, so I put some numbers actually. So imagine that I operated 0.5 and imagine that I am operating somewhere here. Then I increase the duty ratio from 0.6. I am going here. Okay. So now when there is a 0.6, you know that the power is increasing. So this point, the power is increasing. I put here numbers. So imagine one duty ratio are here. The duty ratio increases, you are somewhere here, for example. If the duty ratio increases further, you are somewhere here. So what actually you are doing was, you are changing the duty ratio, then you are measuring the power. Like how you are changing the rheostat and measuring the power. But to understand automatically, so there is a mind action, there is a microcontroller, we program this. So first we will check we will give the duty ratio of the buck converter or boost converter, and then we measure the power. But how actually we can measure the power? So one is two sensors. Okay, two sensors, right? We have a voltage sensor, we have a current sensor. So they are actually putting the voltage sensor and current sensor will be connected to the photovoltaic module. We measure the voltage and we measure the current. And then there is a brain action, so which gives a duty ratio, and then it also receives the information like what is the voltage, what is the corresponding current for the given duty ratio. Then you change the duty ratio. Again you measure voltage and current. For example, if the new power is more than old power, you are going in the same direction. So I start here, one duty ratio corresponding to 1, and then you increase the duty ratio D is equal to D plus delta D and measure the power again through voltage sensor and current sensor. Then again you increase the duty ratio, measure the voltage and current. Like that you go in one direction, and so in the, like when you reaches after this point, so here new power is less than old power. You see, new power is less than old power. So what you do was you change the direction of the surge. So you change the direction of the surge. That means you, instead of going D is equal to D plus delta D, you take D is equal to D minus delta D, or you change the sign of delta D to negative. Okay, then what will happen? You will come to this position. Okay, so what actually we are doing was, there is a PV panel, there is a DC-DC converter, there is a load resistance. So we understand that if I change the duty ratio, then solar panel resistance can be changed. The resistance across the solar panel can be changed. Now we also can measure the power using a voltage sensor and current sensor. You take the voltage sensor, current sensor inputs and measure power for the given duty ratio. Then adjust the duty ratio and see that the power is maximum. That is called maximum power point tracking. Okay. So in a maximum power point tracking, duty ratio is a variable, output variable. The duty ratio is output variable. The objective function is to maximize the power from the PV. So for that we need the data. What is the data? Voltage across the solar panel and current to the solar panel. So we get VPV, IPV using some sensors, and then that we are giving to some microcontroller. In that microcontroller we will write a program. So what is the program? So you send the duty ratio to the boost converter and then measure the corresponding power, and then adjust the duty ratio and see that the power from the solar is higher. Okay, that is called MPPT algorithm. So this is an overall circuit. So let me bring once again. So what we do was, so this is a complete setup. So here we just imagine that now we are taking a boost converter. First we give one duty ratio. So we give one duty ratio, and then there are some sensors like voltage sensor, current sensor. We will give the corresponding power. Okay, so we will have a matrix actually. There is a duty ratio, there is a power. So 0.5, the power is something close to 40 watts. Then we increase the duty ratio somewhere at the station. Increase the duty ratio to 0.6. Okay, now the power is something close to some 70. Okay, because the power, new power is more than old power, I am going the same direction. I am increasing to 0.7, 0.75, maybe 0.75 I am reaching here. Then beyond 0.75 I am decreasing, so new power is not greater than old power, so I change my direction to again 0.75. Is it clear? Like that this algorithm will work. Now here there are two aspects as I told you. One is mind. So mind here is an algorithm, like okay, this duty ratio, this is the power, and other duty ratio, other is the power. But what are the sensors? To compute the power, the voltage sensor and current sensor are the sensors. And what is the output? Output is a duty ratio, which actually is a duty ratio, and boost converter is like an actuator which changes the resistance of the PV panel. Okay. So this is an analogy. Similarly here also, just I want to keep one slide here. There was a conventional vector, the method which I discussed previously is called vector by observer. Means you give a duty ratio, measure power, you change the duty ratio, measure power. If the new power is greater than old power, you go in the same direction, otherwise you change the direction. That's a vector by observer. But sometimes what will happen with the vector by observer is, just imagine that I have now started somewhere new. Okay, so new power, old power. Then once if I change the duty ratio, this becomes new power and this becomes old power. This becomes new power and this becomes old power. Once if I change the duty ratio, this becomes new power and this becomes old power. So what is happening? New power is lesser than old power, it goes to the reverse direction. So somewhere you will be settling here. You will be settling at this point. But it has no intelligence to detect whether it is local peak or global peak. So where actually global peak is here. Okay? Where actually global peak is here, but here if this is your starting search point. So if it is a PNO algorithm, what we discussed, like D is equal to D plus delta D, or d is equal to d minus delta d based on u power is greater than 1 power r. U power is greater than 1 power, we go in the same direction. Otherwise, in the opposite direction. Like how we climb the hill, like we know that the altitude is more, we climb. Then other side it is less. But it don't have any, the PNO method don't have any knowledge about the next peak. Okay, it has only knowledge that u power is greater than 1 power, d is equal to d plus d. Otherwise, d is equal to d. That's all. No other intelligence is there. So, what will happen was, depends upon its starting such point, it may set into a local point. Okay, it is not converging to global point. It is not converging to global point. It is settling to local point. Actually, it is settling here. But actually, your maximum power is somewhere here. Similarly, you take some other curve here. This is GM. But if this is your starting such point, you are settling here. So conventional method, sometimes it gives a guaranteed convergence, sometimes it don't. For example, if it is uniform irradiance, we have already seen uniform irradiance single peak. There is no problem once there is a single peak, because only one peak. If you may search here, or here, whatever, you will somewhere, sometimes will fall here. But if you have a peaks, multiple peaks, then so this may fall sometimes here, or this may fall here. Sometimes global peak, sometimes local peak. So simple algorithms will not work effectively once if you have multiple peaks. Okay. Therefore, we need to use some intelligence algorithms. What is the intelligence algorithm? So have you heard about PSO or genetic algorithm previously? I will give an example because it is very high time if I discuss it. Just imagine that. So there is a gold coin. Okay, there is a gold coin. So like there are some 10 people in the class, in this row. Somewhere it is available that we have to search the gold coin. Okay, the objective is to search a gold coin. Here the objective is to search the location where we get the maximum power. Objective here is finding the gold coin. In our engineering application, the objective is to search the where we get the maximum. Okay, but 10 people, for example, 10 people are searching. 10 people are searching. How they search? They go randomly. Like some people will go right side, left side. They also communicate. Like here it is not there. Some 3 people are. Just for our simplicity, 5 people are searching. One person here, another person here, somewhere there. They try to roam. Okay, and then they communicate each other. They say that okay, it is not available, it is available. Okay, some place they reach and then they can locate basically. Now that is called solution space. I told you within this room. So here also the solution space is a duty ratio because the output variable of the FDP algorithm is a duty ratio. The range of duty ratio is sometimes 0 to 1, for example, 0 to 1. That's a solution space. So like a room here, like a hall, this room is a solution space. Sometimes what will happen was, this is I told you a gold coin in this room, a gold coin in a college, a gold coin in a agricultural place. You find that. So what is the though the objective is to find a gold coin, but the problem is one is to find a gold coin in a classroom, in a college, in a village. So now you see, based on the solution space, which is more problematic. In a village, finding a gold coin is difficult. This divided application. Finding a gold coin in the village is much difficult than finding a gold coin in a similar object, in a hall. So this is easy compared to the other whatever I talked. So the point is that is called. Sometimes we say the function or problem statement, whether it is small problem or big problem, depends upon the solution space. Okay. Sometimes people talk about big problem, so big optimization problem. Okay. That depends upon solution space. Here also solution space is 0 to 1. Okay. So there are multiple algorithms. What actually does was they go randomly within the solution space. They find the corresponding objective function value. They communicate each other and then they travel towards the best solution. Okay? That is how it works. Is it clear? Once again, whatever the algorithm is, I put a example here. So for better understanding. So just imagine that I have taken 3 people are watching. 3 people are touching. In case of genetic algorithms, it is called chromosomes. Okay, in case of particles formation, it is called particles. In case of Kapoor search algorithm, they are called location of the Kapoor. Like that, there are so many algorithms are there, but all algorithms will work like this only. Okay, just I want to give a brief about how the algorithms will work. Whether it could be genetic algorithm, differential evolution algorithm, particles, whatever it may be, the working aspect is like this. Okay, I will put like this. So, though it is a duty ratio, imagine that it is like, though it is with respect to voltage, for our simple convenience, imagine that they are a duty ratio, percentage terms. Okay, so this is our solution space, for example, 0 to 100. This is a solution space. Okay, this is a solution space. Now, I am talking about any algorithm, but how they work. Just I am talking about how they work. Okay, so that even somebody wants to do some research in FDP tracking of different areas, can do it. Now, what we do is we randomly, how do you start your search? We randomly locate different places and then we'll start. Okay, so somebody starts at some 30%, something like 50, something like 82. Okay, these are some starting points. Like you have started your search. Then what we do was you give 30% duty ratio to the boost converter, and then you measure the corresponding power for the picture. How we measure the power? We have sensors basically, voltage and current sensors are there. We measure the voltage and current sensors and then bring the power. So if I bring the power, then what will get what? This is the power I get. What is this power? Close to something some 30 watts. So again, what I do was I will change the duty ratio to 50%. Okay, and then I measure the voltage in that. Once if I find the measure, once if I know the voltage in that, what will happen? I will get a power of something 80 watts. And here, when the duty ratio is 82, I will get a power how much? Something 20 watts. Now, it actually, all the duty ratios will communicate to each other. See, I have 30% duty ratio, but my power is 30 watts. And the other duty ratio, I have 50%, my power is 80 watts. Mine is 82, but my power is 20 watts. So, which is higher? Which is higher? 20 watts is higher, right? That means 82% is more. 82% is giving more power actually. It is giving more power. Then what will happen was, so this whatever other duty ratios, we will try to move towards the better duty ratios. Like we made a formula actually. We can make a formula. So we can make a formula to move towards a better solution. For example. Okay, I put here like this. X is equal to x plus some rad into this is, I put like this is the best duty ratio. Best minus x. Okay, this is a simple mathematical formula. What happens if the rand is 1 to 30? Rand is random number. What happens if the rand is 1? X plus best minus x. What is x plus best minus x? What is x plus best minus x? It is best. What happens if rand is 0? X plus 0 into best minus x is x. That means if random number is there, see, he is having a better, just imagine the place whatever I am talking that stand is there, phone stand. Just imagine that. So above myself and the other person, he has better power, for example. Okay, he is the best person. I mean, he is like that is for best. Maybe he is equal to 82 is the best. Now I am trying to move towards him, but I may fall somewhere here also. Or I may fall beyond him also. Just imagine. And my direction is that side, but I may fall here, or I may fall some other place also. Then what will happen also? So towards that exploration, this may fall somewhere here also. Somewhere here, 85. Then what is the, I find the corresponding power. For 85, the power is how much? 20. For example, 22 watts is the power. 85. 85 is 22 watts. That means the new random position which is fallen may be better than the existing, the best one. The new random number which we got, maybe that means power which is better than the previous better one. Okay? Is it clear? That is how the algorithms will work. Technically, that is a principle. So, that is the population based search. So, initially people will start searching, then they communicate. So, the one which is doing better, the other people will try to move towards that. They may fall into new position, but the new position may be better than the existing others. Like that, this is an iterative process. It will iterate and finally you get this point. So finally you get this point. You can actually moving randomly in a solution space and then try to find a gold point. Similarly, find varying the duration and finding the corresponding power. Then the highest power will use the corresponding duration. Then we will operate at this duration. But this waveform is not known to the this waveform is not known to the microcontroller. We don't know this. See, our eye says that is a peak power, but we don't know that microcontroller don't know that figure. If it knows directly, it can operate this point. I can directly operate at this point, something 90%. But how we are sensing was, so we are just giving a duty ratio, then we are measuring the power. Duty ratio measuring the power, and then we are like randomly changing the duty ratio and then we are measuring the power. Okay, like that if you do some 100 iterations, then obviously you can, because our solution space is very small, definitely this will fall this place. And then already we have a record, actually we store for this duty ratio, this power, this duty ratio, this power. If some 100 iterations we move, definitely we will get one location, okay, where at 82% we have a power of 20 volts. After 100 iterations, what we do was we operate that solar panel with 83% duration, so that we can always get the power of 20. This is how it will work. Now, this is whatever I discussed. This is a problem statement form. Any optimization problem, any optimization whatever you use, PSO or whatever it may be, you will see this kind of a problem statement. Okay, like maximize. Here our objective is to maximize the power of the meeting, subjected to D minimum, D maximum within the solution space. So this is about problem statement. So this is an algorithm like particles of optimization. Of course, I don't want to deal much about this PSO, but the working principle I told you already. So moving randomly, see that we move randomly and then communicate each other. Then try to go towards the best solution. Then if you are trying to go towards best solution, you may fall into a position where you are better than other. Then others will follow you and they may be better than others. Like that, the iteration proceeds. Then you are trying to find the global maximum. Stop here. What is the time now? Yeah, I open for doubts. 120. Any doubts you have? Any doubts you have? Okay, I'll continue for other converters. I'll give a brief about EV, then we'll discuss about the converters of EV. Okay, in case of electrical vehicle, like which motors we use? In case of electrical vehicles, electrical purpose of the electrical vehicle is what? The mobility creates a mobility. Okay? So mobility requires a motor. Which motor we use? Some people say is induction motor. Any other motors? Permanent magnet synchronous. There are two widely used motors. One is the permanent magnet synchronous motor. Other is induction motors. Have you seen the Riva, Mahendra's Riva? Have you heard about it? You don't hear about it. It's the first electric vehicle in India. Electric vehicle manufactured in India. It's not that a demo model. Like it is available in the market. Riva, Mahendra's Riva is the first vehicle. Similarly, you can see some electric vehicles, Viva vehicles in Bangalore actually. They use more actually. Electric period. But nowadays CVs are available in a lot of places. But if you come to technical aspects in case of electric vehicles, induction motors and PMSM motors are widely used. But for tricycle applications, I mean for small vehicles or even for a scooter and all things, BLDC motors are also used. So there are three motors actually. One is the BLDC motors, PMSM motors, and other is induction motors. These are widely used aspects, but for vehicle aspects, induction motor and PMSM motor. Okay. Now, so in case of electric vehicle, you can see here, like the total electric vehicle I have shown as a importance of power losses aspect. One is motor, no, especially for mobility, we need this motor. And similarly, we need a power supply for headlights for different motors. Okay, so that is to supply the auxiliary apparatus, we need a DC-DC converters because usually that requires 12 volts, sometimes 24 volts. But the battery voltage basically is in the level of 400 volts. Like Tesla motors, they operate, the battery voltage level is 400 volts. So this high voltage and then low voltage, the conversion requires a DC-DC converters. Similarly, motors, if you take motors, if you take induction motor, you need to apply V-wave factor to change the speed of the motor. Correct? V-wave factor. NS is equal to 110 for a induction motor. Then if you change the operating frequency, then we can change NS. Then we can change the rotor speed. Then similarly for a PMSM or a BLDC motor, we need an electronic combination. What is the electronic combination? There are two combinations in electrical engineering. One is turning off of the test is one combination. Then reversal of current is another combination. So here, for a DC motor, once if the stator and the rotors are replaced, then we need to give electronic combination. In general, how the DC motor is, what is the stator, what is the rotor? I am talking with respect to armature and field. In case of DC motor, what will happen? The field winding is the rotor and armature winding is stator. So, or reverse. DC, I am talking about the conventional DC motor. Which one is stator, which one is rotor? Field is stator, armature is rotor. Okay? Correct? Field is a stator and armature is a rotor. In case of conventional DC motor, you have studied this in second year. DC motors. Field is stator and armature is rotor. Okay, then we have a slip rings. Correct? You have slip rings. Then once the motor is rotating, that slip rings will come into picture. That does the combination. So outside is DC, but the armature field is armature actually experiences AC. But if I want to change the stator to rotor, because there is an advantage if I bring the armature to stationary and field into rotor. Okay, so here the field is not there. We are not exciting. So in case of permanent magnet, we are creating the field using permanent magnets. There is no electromagnet there. We are directly giving a permanent magnet. So that becomes permanent magnets. But whereas the armature we made in stator. But if I made it to stator, then what you are supposed to do is you have to create the area flux as sinusoidal. You have to create a flux, sinusoidal flux you have to create to see that is also rotating a smooth torque. To create that sinusoidal flux in the area, then you should give the once again a electronic. There are some windings actually. We need to see that the windings are excited properly so that we will get a continuous torque. For example, imagine that I have some 6 windings. Okay. Imagine that I have 6 windings. This is a normal exposure. Okay. Then opposite pair of windings should be supplied such that we get a continuous smooth torque. For example, this is a first. Imagine that the power is a north pole, and then left side of the power and then right side of the power. If this pole becomes south and this pole becomes north, you know that one is attracted, one is rebel. Okay, so and it is the direction is in one direction. Just imagine that right side is this side. About this side is this is a north pole. This is also north, and the opposite is south. Then it tries to move in this direction. Now what you do was, when you are here, you try to extend the similar way. Like this becomes north and the other becomes south. So here ripple and then their attraction. So it moves like this. So if you imagine that the pole positions are continuously changing to ensure that same torque, okay, then we can say that it will rotate properly. Correct? So here the concept is we have to excite the windings at the given location. That's why PMSM motors have sensors which will sense the locations of your motor. Have you seen BLDC motor or PMSM motor? It has some sensors which will talk about the position. Based on the position only, we should excite proper winding. To excite the proper winding with the two directions of the current. Sometimes we need to make one pole, one winding as an north pole, sometimes the same winding as a south pole. How can I change the same winding as a north pole and south pole? By changing the direction of the current. So you need an inverter operation there also. So to create an electronic computation. Therefore, inverter kind of setup you see here. Inverter kind of setup is shown here. See. So this is basically to provide electronic computation, proper electronic computation, so that you can reduce the torque continuously. Is it clear? To reduce the torque continuously. So here is one area place, area where people are working especially for driving the motor. So one of the most important aspects is to drive to give the load torque as per the electrical vehicle demands, and other aspect is to see that the torque ripples are very small. Okay. When it comes to motor, you are actually devising a inverter for that. So what is your focus is you see that the flux gap it can be sinusoidal, which ensures that your torques are having less ripples. For example, just imagine that I have an induction motor. If I excite the induction motor, then what will happen was induction motor experience continuous torque, almost constant torque. But in the same AC supply, if I given AC supply, what will happen was it has pulsating torque. Okay, so leave that apart. When we are designing any inverter, so you should ensure that, especially for the motor application, you should ensure that the torque ripples are very small. What do you mean by torque ripple? What do you mean by torque ripple? If for example, the torque is constant, your drive performance is smooth. But sometimes if the torque ripples are there, like it will be like this. You move far like that. You know that torque ripples are like, it will impact on the engine, total motor. It will damage the motor permanently. So you need to ensure that for a motor, torque ripple should be very small. Like I told you, for a DC-DC converter, DC, you should have lower ripple. When we are talking about AC, you should have lower TSD. When we are talking about motor, low torque ripples. They are some requirements. See, everyone will design for this. Everyone will design for this. Low current ripple for DC side, low current ripple. Okay, then AC side, sinusoidal currents. Okay, then motor, reduce the torque. This is about electrical engineering. So ensure that when you are designing DC supply, you see that the load currently has reduced voltage ripples. If you are designing a motor driver, you see that the motor is performing well by giving a continuous torque or constant torque. If you are drawing a current, then you see that the current is sinusoidal current. Okay, these are some requirements of any converters in the electrical vehicle or even in power electrons, whatever. So in the course of time, we will see like how do you meet that requirements. Okay. How do you meet that requirements? We will see the afternoon session. Thank you. Any notes? Okay, so in the morning, what we discussed is we discussed about the PE. Then we talked about the degeneracy analysis, importance in the maximum power factor. Right? So now we discussed about the buck converter, boost converter, then buck boost converter. So sometimes we need to increase the voltage. Like we have seen in case of a buck converter, the duty ratio is given by V. The relation between the output voltage and input voltage is given by V naught is equal to D times V. Right? And similarly, for a boost converter, we have seen that V naught by V. What is V naught by V for boost converter? One by 1 minus C. So here gain is equal to 1 by 1 minus T. But what is the range of iteration? 0 to 1. So gain can be infinite. Ideally speaking, gain can be infinite, right? So gain can be infinite ideally, but for a boost converter, the maximum gain is any idea? Maximum gain is 5 ohm. For a boost converter, the maximum gain is how much? 5. So what will happen was, of course I have there is no waveform here, but I will just put a waveform here. What will happen was, if I just plot a gain with respect to duty ratio, this is close to 0.8. So basically the duty ratio increases, then gain increases. But at t is equal to beyond 0.8, gain basically decreases. Because previously we assumed that all of the elements like inductor, switch, diode, they are ideal elements. But in practical inductor, what is inductor basically? Inductor is like bounded wire is inductor. Bounded wire is inductor. Wire do have resistance, so inductor do has some resistance. So what will happen was, there is a voltage drop appears in the across the inductor, physical inductor, because it has resistance. Similarly, we have seen in a boost converter, okay, so one is source, then like this we have seen it. Diode also has that. Diode do have some constant resistance. So diode has constant resistance, switch has constant resistance. So if there is a resistance, then there is a voltage drop. So whatever the voltage we are talking about in terms of formula 1 by 1 minus D into V, V naught is equal to V into 1 by 1 minus D. It is not correct actually. The practical voltage V has some parameters which is influenced by RL and RR. This is the resistance of the inductance and the resistance of the diode plays an important role. What will happen was that because of this resistance, even as per our gain says that if the duty ratio is increasing, the ideally gain should be increased the highest value is infinity. But in practical case, the voltage gain is limited to only 5 ohm. Only 5. Okay. But sometimes, we have to bring the voltage to 600 volts DC because to inject the power into the grid, we need 600 volts DC. But sometimes we have a low voltage. Just imagine that 6 volts is our voltage. Especially fuel cells, they give very low voltage. So to bring the 6 volts to 600, then how much gain is required? 100 gain. So sometimes we need to increase the voltage gain. So some of the research, so whatever I am talking about is, so some of the research aspects of DC converters. One is wide range of operation. Other is bidirectional utility. What is meant by bidirectional utility? A converter is there. Okay, so we have drawn previously. So two ports are there, right? One is input port and the output port. So you ensure that the power can be transferred between A to B or B to B. Like that is for bidirectional process. So the transfer of power should be in both directions. That we say it is a bidirectional DC. Okay, this is it. Similarly, reduced ripple current. I told you right. For a DC, the important parameter is what? Ripple current. You need to see that the currents should have lower current. The converter what you are designing should have lower current. For inverter, lower PSD. For a DC converter, lower current. These are very important points. Then sometimes we need a isolation. Electrical isolation should be required between load as well as supply. Electrical isolation means what? What is the electrical isolation? Right, transformer is basically one device there, usually talk about, which is magnetically coupled, but it is electrically isolated. Okay. Some applications actually design the feature, electrical isolations. Similarly, like whenever you are developing, input efficiency is one of the design parameters. Some people will develop the converters towards improving the efficiency. Okay, now this is a simple bidirectional converter I have shown you, but of course there are so many bidirectional converters available in the literature. I will just draw the buck converter and boost converter, and then you can realize what is this. What is this converter? Boost converter. Now, so here you see, whenever we are talking about a bidirectional converter, we should not talk like the input or output. Our terminology will change like B low, B high. Okay, like one is low voltage DC bus, other is high voltage DC bus. Okay, one is low voltage DC bus, other is high voltage DC bus. Now you can see from this aspect, this angle you can see. From this angle, from this aspect, from here you see VH to VL. If the power has to be flow from VH, high voltage to low voltage, which type of converter we will use? Otherwise, high voltage to low voltage. It's a buck converter, right? So here you can see the buck converter has a series switch and then parallel. You see from this, you have S1 is a switch. And then S2 diode, you see S2 has diode, parallel diode. S2 diode is like diode. Now you see the remaining circuit, everything looks same. But you see the circuit or you realize the circuit from this angle. If you realize the circuit from this angle, it looks like a buck converter. Okay, it looks like a buck converter where we are giving a PWM to S1. This is buck. Now you see from what will happen was if you are giving a PWM means on sequence. Then it acts like a buck converter. The power flows from VH to VL, high voltage to low voltage. But instead of that, you see from this angle from here, instead of S1, if I give a PWM to S2, And then if I am using the S1 body diagram, this is the body diagram. S1 body diagram. If I am giving the PW to S2, and if S1 is a body diagram, what will happen? It is exactly like a boost converter. You can see here. This is like a boost converter. You see, boost converter, inductor, switch, then the body diagram of S1 body diagram. Then capacitor and then resistance. Okay, clear now? So depends upon which you turn on, which you are giving PW, then you can make the power flow from BH to BL or BL to BH. One time it is bucking, means we are increasing the voltage. Other time the same converter we are able to boost. Okay, clear? From A to B, if it is buck, B to A it is boost. Okay, especially in case of electrical vehicles, we usually use two kinds of batteries. Two batteries physically we use. One is high voltage battery, 400 volts. Other is a low voltage battery, some 12 volts. Okay, 12 volts battery. So sometimes we extend the power between BH to BL, mostly from BH to BL only, but very less. Percentage is very less. We convert from BL to BH. Okay. But so this feature is essential. So bidirectional feature is essential in case if there are two batteries and the battery voltage depends upon one of them. Okay. So especially for regenerative operation also. What is mean by regenerative operation? Like you have to sometimes charge the battery. It's not always that you discharge the battery. You have to charge the battery. You have to take the power into the battery. Then the bidirectional ability plays an important role. Okay. Clear? Then I told you I always talk about DC current levels, right? So DC current levels. Because for an inverter, we know output is TSD. The quantum of the quality of output is TSD. For a DC converter, it is Ripple. Okay. We have seen when we are talking about the boost converter, we have seen that when just imagine that I am just plotting once again a boost converter. Okay, so if the switch is closed, we know that delta VL is equal to V in, the current will be like this. You have seen in the steady state images. Have you seen this? You have seen, right? This is IL. IL is like this. But a power supply, we have a lesser, which means always what is actually we anticipate was we want only constant current. This is our ideal current phase shape. But what we are doing was we are actually switching. So the current shape will be like this kind of current shape. But you need to reduce the ripples. Okay, to reduce the ripples, people has come up with a concept called interleaved converter operation. What actually we do was we connect two boost converters in parallel. That's all. You see here, this is one set of boost converter, L1, S1 and D1. Other set of boost converters L2, S2 and D2. So what we do was, you can see here, IL1 is drawing from first boost converter, IL2 is drawing from second boost converter. So what is the total current I? It is equal to IL1 plus IL2, right? So this current I am talking, the total current is equal to, if you apply KCL at this node, okay, assuming that the capacitor is 0, IP is equal to IL1 plus IL2. Then, you see here, this is IL1 and this is IL2. Then the IL1 plus IL2, you see, whatever is the delta I, so here the delta is reduced to half. So what you are supposed to do was, here if you are giving a PW, okay, like this. For S2, you should give a PW with the 180 degrees phase shift, okay? 180 degrees phase shift means, for example, like this is R off. You give 180 degrees phase shift. If you give the 180 degrees phase shift, then you will see this kind of currents. IL like this, IL like this. This waveform also 180 degrees phase shift. See, the two triangular waveforms, they phase shift by 180 degrees. The resultant wave shape triangle has delta A, which is half of the previous one. That means if this is delta I, okay, this ripple is reduced to delta I. That means you are basically reducing the ripples by connecting the two boost converters in parallel. Okay, but you are also operating at 180 degrees phase shift. Then the resultant ripples are reduced. Okay. Similarly, buck converter. if you want to reduce the ripple further, then you can add one more what to say boost converter parallel like L3, D3, S3 also will come, and you operate the 3 with how much phase shift you have to operate. If I use 3 boost converters, then S1, S2, S3 will come. Yeah? If you want to see that the current ripples are very small, then how much? What is the phase shift? It should be 100 degrees. Okay. So like that, it is like. Can you give a relation between the number of boost converter and the required phase shift? Required phase shift. For a given number of boost converters, required phase shift. 360 by n, correct? 360 by n. So if you take 360 by n phase delay between the switches, then we can reduce actually the ripples. The same thing applicable for buck converter also. Buck converter current waveform is like this. It's not even like this. It's like this. This is the buck converter current waveform, input current wave. But if it is phase shifted by any 180 degrees phase shift, then total current is how it looks. Looks like this. This is I1, this is I2. This is I1, this is I2. So here you see there is a large ripple is there, but you can avoid the ripple by using interleaved operation. So interleaved operation will help us to reduce the ripples. Clear? So this is how we can able to get a constant current going more number of converters. For this the gain is same only, 1 by 1 minus d for it, boost converter and d into d in this one buck converter. Then, as I told you, like sometimes we need an electrical isolation between load and source. Then which device we use for electrical isolation is a transformer. But transformer here there is a difference between this transformer and the transformer what we are using. This transformer is operating at a frequency of something like 20 kHz to like 200 kHz. But what is the power frequency of the transformer what you are using? What you are using? 50 Hz, right? The power frequency of the transformer is 50 Hz. You can imagine like this. So there is a bucket full of water. Okay. So you have to. One is this is 1 month. Okay, for 1 month. Other is this one. So one is 1 month. Okay, just realize like it's full of water. Like you need to empty the bucket. That is your problem statement. So you have to fill up bucket. Like you need to empty the bucket. One is 1 month and 1 month. So just imagine that the time. I am just ensuring that the time should be same, and you need to see that with 1 month and 1 2. I need to see that within the given time. So I need to make the bucket empty. It's not like reversing, but I need to use only 1 month and 1 2. There is no drill and nothing is there. I need to use only 1 month or 1 2. Then this frequency of operation. The frequency of operation should be such that you should do it very fast, so that within a timeline, with the same 1 2, I can actually make it 1 1, right? Correct? So the point is, if you there is a water bucket with full of water, then with one bigger mug, then what you do was you can actually do. That's for power. That's for big transformer with T frequency. But we are doing that operation very slowly. But if you take small transformer, but if your operation frequency increases, okay, then you can make the bucket so empty. But the only thing is you have to see that the operation is very high. Operation frequency is very high. Similarly, in case of a transformer also, in case of transformer, if you take a power frequency, we need a large value of transformer. The size of transformer is very big to transfer one quantum energy. But in the same transformer, if you operate higher frequency, that means you are actually changing, you are giving from primary to secondary, and then secondary energy transfer you are taking at very fast rate, very fast rate. Then the size can be size of the the transformer can be reduced. So here also, when it comes to DC-DC converter, the input is DC, the output is DC, but we excite that. So using a transformer, but this frequency of operation is very high. Usually you know that if the DC is given to transformer, the final value is very high, then we have studied that. But here what we do was, so we give the change in voltage by closing and opening switch at very faster rate. At very fast rate. Okay? So that the same isolation we can use for DC-DC converter, but the operation frequency is very high, so that we can able to transfer the power. So one supply to other supply, but again we have to bring it back. As I told you, you should use LC method. So here we use L and C. Then up to some something like if any converter is there, then it is important for you to understand what is its efficiency with respect to the load power. Okay. So further we need to do, there are two parameters. One is conduction losses, other is switching losses. Conduction losses depends upon its unstable resistance, and switching losses depends upon on time and off time. Okay. The switching loss of the power converter depends upon on time and off time, and the conduction losses depends upon the constant resistance. Similarly, diode do have resistance. One is due to forward voltage drop, other is due to internal resistance. Okay. Then the inductor is also, as I told you, it has some binding resistance. So to accommodate the losses, then inductor power is given by L square is order. If I am using two inductors, then we add P1 and P2. Similarly, capacitors. Capacitor, capacitor basically it's a direct between the two parameters we have there. So, but even if you use, ideally speaking, there is no current should flow from positive plate to negative plate. But because it's a practical device, it's not ideal if you consider. Then there is a small leakage current. So because of that, there is a small resistance actually. That is called ESR. We call that as electrostatic resistance. Every capacitor do have ESR. You can actually find the ESR values and inductor resistance values using LCR method. I think you might see LCR method in your labs. Okay, through that LCR method, we can actually measure the capacitance resistance as well as capacitance values also. Okay, and then to compute the efficiency for the given MOSFET, if you see the MOSFET, anyway I will show you later. For given MOSFETs, they will give the data sheet will give this parameter like RDS on time, off time. Similarly, the data sheet of the diode will give the RD on state resistance and VF. Okay. So now, so you can take this this slide. Like what is the slide is mostly like if you take any power devices, reliability plays important. What is in the reliability? Reliability. So we say that one system is, if I say more reliable, it is less strength to fault. I mean, it works in a proper way. Most timely and respect time it works in a proper way. So here I just kept you one slide indicating what is the importance of temperature. See, especially semiconductor devices. If you talk about power converters, semiconductor devices and capacitors and inductors are the most dominant inputs. Switches, inductors, capacitors. Out of all, switches are the primary reasons of failure of any semiconductor devices. Switches, then capacitors. Inductors are less tend to fault. But switches and the capacitors play an important role because the switch is basically semiconductor devices. They are more prone to fault and they are more sensitive to temperature. So, for example, if the temperature is if it exceeds beyond 100 degrees centigrade, it will fail. So that is why if you see, if somebody sees the power converters, we use heat sinks actually. Because I have already told you that the switch has some RDS loss, switch has some switches loss, switching losses. Then what will happen was whatever the power wasted, that is converted into heat in the switch. That heat has to be dissipated outside to the environment so that you can maintain the temperature within the safe limits of the thyristor or whatever the switch. So in order to do that, basically we design the heat sink. So I think you might see about a different form of transformer. Usually transformer closely the distribution transformers I talked about. So where you see the bigger, like a tubes will come into the picture, right? Because the transformer dissipates some energy of heat, then it should bring back to the environment. Otherwise, the transformer will get spoiled. So similarly, the semiconductor devices are more sensitive to temperature. You need a heat sink, so it should be exposed to the environment, and you should ensure that it is though one side you are getting losses because of switching losses and convection losses. The same energy which is accumulating will tend to raise the temperature. If it rises, then you experience switch failure. But at the same time, if it released to the environment, right? So the switch can be maintained in the same region. To demonstrate the importance of the losses and the importance of junction temperature, these are some formulas. Okay, no need to bother about all these things. But out of this slide, what is the important parameter which I want you to understand was, so the failure of any switch was modeled. So you can see the failure of switch depends upon pi. This is the most important parameter. So other parameters are like application where you are using. For example, sometimes you are using a harsh environment. For example, if it is a space has a lot of electromagnetic noises over there. Okay, like that some vibrations in some applications. So remaining parameters are specific to application, but most important parameter of the failure rate which is which is nothing but temperature parameter. So temperature parameter plays an important role in semiconductors. Okay. So this temperature again depends upon the losses. Again depends upon the losses. You can see here. So if you try to reduce the losses, then you can maintain the safe operation of semiconductors. Okay. Now the agenda is to develop some different converter topologies to ensure that lower losses occur, so that the total the system can be made safe. So once again, so in case of semiconductor devices, temperature plays an important role. We need to reduce the losses. If we reduce the losses, then we can say that the semiconductor device is safe. Okay. Okay. Before going to soft switching and not, actually, what will happen once if you open the switch? What is the switching losses? That we will see in a minute. So just imagine that this is a previously the voltage is like this. Previously the voltage is like this. Okay. If the switch is given PW, PW means high. PW means gate pulse if you apply, then what will happen is it comes to zero. The voltage becomes to zero. Similarly, current also previously when the switch is open, current is zero. Current is of course not completely, but very small magnetic leakage current will be there. But after a time, after some time, it will rise. This is the current line. So the current will be like this. Voltage will come to zero. Okay. This is the transition. This is the waveform transition from off state to on state. Ideally speaking, what we have assured previously was if the voltage, if the switch is open, the current is zero. If the switch is closed, the current is. If the switch is open, the current is zero. If the switch is closed, the voltage is zero. So V into I is zero. That's what our assumption is. But in practical, there is an RDS on. Okay. Similarly, there is a leakage current. And similarly, during on time and off time, there are some losses. So to show that I have shown the voltage across the switch current to switch. If you plot V into I, what will happen was you will see this kind of relation. V into I am plotting. So you can see here. You see here. This is actually losses. Losses during switching. This is how the losses are there during switching. Similarly, if it is off to on again, there is one more switching is there. Okay, this losses will experience. But one hand, what is the on one hand we have talked about the advantage of increasing frequency. That is to reduce the size of L value or transformer. We have told right the power frequency, whatever the energy to be transferred. Okay, is the size is very small for the 50 kHz frequency. Whereas 50 if it is required bigger size, if you are operating the same transformer at 50 kHz, the size of the transformer becomes this much. So one advantage of increasing the frequency is to reduce the size of the switching high frequency transformer inductor size. But the one drawback is you see the lot of losses because during switching you will experience more loss. Okay, this kind of losses you will experience. It depends upon switching. I mean, how many times you are turning on turn off. So that depends on the switching frequency. That influences the switching losses. Okay? More switching frequency, more switching loss. So to avoid this, people has come up with some new converter technologies. Of course, I talk about only the basics. Okay. So what we do was, this is a somehow this is a voltage current. How do you reduce the switch losses? To reduce the switch losses, what you do was, you do some circuit modification and see that you ensure that the current starts after some time. That means instead of starting the current immediately when the voltage starts decreasing, you see that you ensure the current rising happens only after the voltage comes to zero. Means like this is voltage here, and this is voltage here. If you ensure that the current starts after some time like this, then basically there is no switching losses. There is no switching losses. This is called ZBS operation. ZBS, zero voltage switching. That means before giving the PWM to the switch, you are making the voltage to zero. Then you are reducing the losses. This is called zero voltage switching. And similarly, another way of changing the another way of decreasing the voltage is you try to change the slope. So, for example, previously this is the slope. If you are decreasing the slope, then also you can actually reduce the losses because this period has low losses. Okay? Like that, you are actually changing the shape of the current. Shape of the voltage. What are the fundamental way of, for example, either waveform is there, but how do you change the shape of the current? You take proper LC values, and then you see that we know that some relations like when omega switching frequency is greater than resonant frequency, then we can make the current lagging. Similarly, you can make the voltage leading by taking omega naught, omega s greater than omega naught, like lagging and leading nature. We know inductors are true. In the capacitor circuit, we have studied in BTech third year, right? And in circuit theory also. The same aspects we use here, and then we try to develop a topology here. So this is basically a full bridge resonant converter. Okay. So how many have seen this waveform, this series loaded resonant converters? Somebody is doing project here. Anyway, so what we do was, here we have a inverter kind of setup will be there. Okay, this is an inverter kind of setup. So once if you close S1, S2, you get VDC. S3 and S4 is closed, you get minus VDC. But S4, S4, S2 or S4, S2 if they are closed, then you get 0. Okay, so out of this DAT can be a square waveform like this, or it can be a quasi square. What is quasi square waveform? Which has some zero quotient. Like this. This is how VAB will be there. So you know that what is that this is VAB1 and this is VAB2. What is the fundamental waveform? Fundamental magnitude for this VAB? It is 4 VDC by 5. How many of you know? A square waveform fundamental quantity is how much? 4 VDC by n pi when n is the harmonic. Like if n is 1, then you get 4 VDC by 5. So here this into cos alpha, like this is alpha, it is alpha. Okay, this is alpha. Cos alpha. So VAB2 is equal to VAB1 into cos alpha. So cos alpha. The point here is we can change the voltage by giving it by making it either into a square waveform or quasi square waveform by changing the phase angle of alpha. Okay. Now, so here if this is how we can vary VAB, then the same thing will reflect on V0 also. See, this is V0. So this is what we are doing. Here we are doing AC, again we are converting back to DC. We are converting back to DC using a simple diode multiplier. You see, this is a diode multiplier, right? This is a diode multiplier. Okay. But here, what we do was, so what is the difference between the previous converter and this converter is, in the previous converter we use hard switching. That means whatever the buck converter we are talking about, the buck converter is like this, right? This is a buck converter. Okay, this is a buck converter. Here, whatever we are talking about is a hard switching converter where you experience more losses. But this converter has low losses. Okay, so what we do was we basically create some wave shaping, and we see that the during the switch on, we ensure that ZDS operating express. I feel like this is more for you to discuss, so I was skipping this slide. Of course, sometimes we also use resonant converters, especially for isolation. So as I told you, like sometimes we need to create a isolation. So in between, you can see that there is a high frequency transfer. There is high frequency transfer. Okay, so with that high frequency transformer, with the proper switching, then we can achieve ZDS, zero voltage switching, as well as we can transfer the power from one to one. And then the range of step up or step down can be improved. See, if you properly select NP and LS, then we can increase actually the range of resonant frequency. So this is supposed to be okay. So till now what we discussed was most related to DC converters. So those who are thinking now, you can take, this is a new topic, like this is again fresh. Okay, so take a small break. Over. Again that one. This is a new topic, right? So till now what we discussed was about DC converters. Some requirements, of course, they are still in the research link. If some people are really interested in doing research in the so there are a lot of areas actually. People are still working in improving the reliability. They are doing the different circuit topologies, especially in improving the voltage gain or bringing the validational features or improving the reliability or improving the efficiency. So much work is going on. Okay. Now this one is basically our DC AC converters. Of course, especially for the in case of PV, we have DC supply as I told you. Then from the DC we have to inject into the grid. Grid requires what? Grid is basically AC. So for synchronization, then again we need an inverter. So further we are talking about a simple DC AC conversion. Now you see, this is a new topic. So please be able to, you will get something out of it. Listen. Unlike simply speaking and thinking about something, better you just focus on this. Definitely you will get some idea or insights into your projects also. I can assure you. Okay. Imagine that this is green. Okay. Imagine that this is green. So if this is 0 and I have this connecting this like this. This is a point E. So VA0 usually called as pole voltage. In inverter, between capacitor, like we generally take, of course, it's a fictitious point only. Capacitors need not be always, capacitors need not be there at 0, but it's a fictitious point. Just to understand how they work, so we always talk this aspect, like we take two capacitors and then we take the midpoint of the capacitor. But it will not be there. It is not physical, it is not existing. But for understanding, we need to use a fictitious midpoint of the capacitor. Okay. Then if S1 is closed, okay, what is VA0? Okay, let me put like this is a V here, like some 100 volts. Then if we keep two capacitors, then this capacitor is VD by 2. This capacitor voltage is again VD by 2. Okay, satisfying the KVA. Now, if S1 is closed, what is VA0? So, plus is connected to plus and minus is 0. So, VA0 is VD0. If S2 is closed, okay, minus is connected to A point, plus is 0. So, VA0 becomes VA0 becomes minus VA0. Okay. So, as I was showing, sometimes so VDC by 2, sometimes minus VDC by 2. Okay. So you are getting two voltage levels, therefore it is known as two level. Okay. If S1 is closed, you will get VDC by 2, and if S2 is closed, you will get minus VDC by 2. Okay. So this is, I am talking about only one leg in inverter. In a one leg, if midpoint you are taking this point, one pole, this is called one pole. VA0 sometimes it is plus VDC by 2, sometimes it is minus VDC by 2. Okay. Now, so what I do was usually, one is but if you want to get zero voltage also, like, if you want to get a zero voltage, then what you can do is you can have another S1, S2, but you need to tap the midpoint. So for that I have shown something like this. Midpoint also if you tap, if it is somewhere here, S1, then you get VDC by 2. If it is here, then this position, not the positions, whether this is A or something like even B2, position 1, position 2. So when this is A and with respect to midpoint I am talking 0. Okay, if it is at P1, then you get plus VDC by 2. If it is at P2, you get 0, and if it is P3, you get minus VDC. Okay, minus VDC. So actually, what we are doing was, I have just discussed till now is a couple of switches and a voltage between the midpoint of the capacitor and a pole. So with that, what we can do is sometimes we can get VDC by 2 0 minus VDC by 2 or VDC by 2 minus VDC. Now, in general for inverter, what we do was, so there are two types of waveforms we usually do. One is called carrier waveform, other is reference waveform. Okay. So before progressing into the discussion, generally what is the voltage level? I think you might see about a simple inverter, right? This is simple inverter. This is simple inverter. Okay. Simple inverter, I think which you have studied, a simple single phase inverter. So input is DC supply. Now, what is the flexibility as we have S1, S2, S3, S4? Just imagine that this is the load here. S minus VDD is the load. Okay, this is the load. Now, if S1 and S4 is closed, then we get plus VDC, S3 and S2 minus VDC. Okay. Now, we have only luxury to change the voltage, either it is plus VDC or 0 or minus VDC. But what is our anticipated AC voltage? Once again, see, if S1 and S4 is closed, we get plus VDC. Inverter, general inverter, you know this, already you know this information. If S1 and S4 is there, if S1 and S4 is closed, you get plus VDC. S3, S2 closed, you get minus VDC. S1, S3 or S2, S4 is closed, then you get 0. These are three voltage levels only. But what is our anticipated voltage level for a sine waveform or for a AC waveform? From the inverter, what is that you are expecting? From inverter, what is that you are expecting? inverter, DC, AC converter. What is the pure expectation? No one gives this answer. See, once again, for inverter, what is the waveform you are expecting from the inverter? Sinusoidal waveform. Okay. So I am expecting sine wave. But what is the voltage levels we have available? What is the VDC available? VDC 0 minus Vs. But our expected voltage is Vm sine omega. But you have VDC 0 minus Vs. Then how do you get it? How do you get a sine wave? How do you get it? Is any wave shaping we are doing? We are not doing any wave shaping. So after the switches, the switches are closed. We get there are three possibilities. One is VDC 0 minus VDC. But what is the shape we are expecting? Sinusoidal. But how do we get this? So the way how we can get was, you can see here. See here. You give the pulse. I mean on time. Just see here on time and off time. See, just give the pulse on time and off time to realize like a sine wave. For example, if you see here middle part, I mean it's completely on time. Okay, you try to dissect it. So instead of a simple, complete waveform, you dissect the waveform. So like this. So here, if you see here, like less on time, more off time. Like that, if on time is increasing, what is happening at the end, at the middle, you try to realize that bigger waveforms. If you do the average waveform, if you do the averaging aspect, if you do the average, you will get a sinusoidal waveform. Average form. If you take the average, you get sinusoidal. That means what we are actually doing was, we are giving a PW and the duty ratio is like a sine wave. Okay, so if you give a PW which realizes the duty ratio to be sinusoidal, then the average value is a sinusoidal. Okay, but the instantaneous value is VDC is 0. VDC is 0, VDC is 0, or VDC by 2 whatever. But if you take the average value, if you give a LC filter, if you use a small LC filter, it actually can shape the current and voltage as a sine waveform. So this is how we will give a PW. Okay, further to give a PW, then what you are supposed to do was, there are two types of signals what we do. One is called carrier signal, one is called carrier waveform, other is reference waveform. Okay, so what we do, we take some triangular waveform, and then we compare this with a reference waveform. And then if reference, for example, reference waveform is greater than triangular waveform, we give the PW to first switch. Otherwise, you do the NOT operation and give it to the lower switch. NOT operation is complementary to each other. Give it to the lower switch. If you do like that, you will get the similar shape what I have drawn in the previous. So if you give a sinusoidal waveform, you will get average value sinusoidal waveform. If you give a, here instead of giving a sinusoidal, if you give some other shape of the waveform, like a triangle, you will get the average value of the triangle. So the reference waveform decides the actual waveform. Because of that, we are applying for a sine PW technique. The reference waveform we are doing sine, because we need a sine waveform. We need a sine waveform. Therefore, because of that, we give a reference signal to the sinusoidal waveform. Because the actual signal, the average of the actual signal follows the reference signal. If it is sinusoidal, the average waveform on output voltage is also a sinusoidal. If it is triangular, it will be triangular. Okay. So here, like this, we generate a PW for a given input. Okay. For a given input. Now this is a three-phase DC-AC conversion. You can see here I have shown. You can see here. This is a two-level, three-phase two-level. Okay, here I am talking just to VA0. VA0. So this is I'm keeping instead of VDC 2 VDC. I kept 2 VDC so that this becomes VDC and this becomes minus VDC. Just 2. You can also realize like this. We also realize that this they keep like 2 VDC. Or you can keep this as a VDC and this becomes VDC by 2 and minus VDC by 2. Okay, both are same. But what is the voltage? Here I am talking about VA0. So one pole voltage I am talking about VA0. So if S1 is closed, you will get what? VA0 is plus VDC by 2. And if S4 is closed, you will get minus VDC by 2. Okay? But between the two poles, you will get like this. So positive negative, there is no zero moment. So because you will get either VDC by 2 or minus VDC by 2. Or VDC or minus VDC, this is 2 VDC. So if PWM is applied, you can see here, you have 2 levels over here. There is no 0 level. So for a core voltage I am talking, for a core voltage, once again, if this is 2 VDC, if the A is connected to here with respect to A0 it is plus VDC, with respect to A0 if S4 is closed it becomes minus VDC. 2 voltage levels are only there. VDC minus VDC. Now you see here, if you closely look into this, with the same voltage level VDC and minus VDC, we can actually generate the average value sinusoidal. Because you see in this point, negative voltage is very small, but the positive time is very high. But you see from the other end, this side you see negative voltage level is very high and the positive voltage level is very short. Like that, if you see the average value, it will be something close like this. So during negative peak you have more negative, during positive peak you have more positive. Within 2 levels we can able to realize the sinusoidal. Okay. For the same thing, if I want to realize multiple levels, then what you are supposed to do? So you should have some other switch to tap this zero potential also. Previously VDC minus VDC is there. So if you want to have more level, then you keep 0 also like this. But if you want increase more voltage levels, then you keep few capacitors and then try to tap the voltage here. That means if you are having more voltage levels, actually you can bring more sinusoidal waves. If you have more, see, previously it is like this. I mean only 2 levels. But if you have more levels, then you can bring more sinusoidal wave or near sinusoidal wave. So that is why multi-level motors people are using. So they find a lot of applications. So some of the conventional multi-level motors like cascaded and then flying capacitor and neutral point clamp. I am not detailing much, but this is how it looks. Okay. Then AC/DC converter, I think you have studied this before, noise. Especially like when there are multiple AC/DC converters available. This is a full controlled AC/DC converter where so you have a positive voltage signal, you have a negative voltage signal. Then by changing the firing angle, you can actually change the output voltage. You see, the output voltage you can actually change it, okay, as per our design. The firing angle is the one which will influence the output voltage. We put it to cos. Then so if I talk about a single phase rectifier operation, because why I talk about the rectifier is especially in case of electric, we need to draw the power from the grid. So we need to draw the power from the grid. So for that we need to know about the operation of the rectifier. So have you seen this rectifier previously in your power towns? Have you seen a diverter rectifier? Have you seen? So if it is a diverter rectifier, okay, what will happen was this is a input current for example, but the current waveform, if you see, I will put like this. This is a this is input voltage, but after rectification it becomes unidirectional. But imagine that this is the output voltage V0. So you have connected a large array of capacitors, and this is a V0. So these diodes will be forward biased. For example, in the positive waveform, usually V1 and V2 will be forward biased. Right? Provided if input voltage is higher than the capacitor voltage, then only it will be forward biased. Otherwise, all of them are reverse biased. So only portion which the forward bias is this one, the current will flow like this. Okay? And similarly, the input current, if I draw, it will be like this. It means the current shape is like this. From the grid, you are actually drawing this kind of a current. But what is the power factor formula? Power factor is given by distortion factor, displacement factor. Okay. So displacement factor, though you assume that is unity, but the distortion factor depends upon the quality. It is not actually sine waveform. You have to draw the sinusoidal currents. It's not a peaking current like this. What is the reason for this current? Because during that region only, the diode becomes forward bias. Only that the input voltage is higher than output voltage. During this region, only because of then only at that time only the current, the diodes are forward bias. Therefore, current will be flowing. Unlike this, actually, what is designed is a sinusoidal wave, sinusoidal current. Okay. How it actually flowing is a pulse timing, like a peaking current it is flowing. Okay, you try to simulate in MATLAB, you can see this kind of a current, which is not desirable in case of when you are drawing high current, because the charging is for electric vehicle, you are charging it at 50 amperes or 30 amperes or 10 amperes. It's a higher value. What is our fuse rating? 5 amperes. Imagine it is 10 amperes or 15 amperes, it is very high current, right? So you should not draw the current like a peaking waveform. So you will be paralyzed because the government will paralyze you. With being your the supply is not good. I mean, what you are drawing is very bad, and is very bad. So the government will paralyze you. So the energy meter what we have, that will also reflect what is the quality of disturbance you are creating. Okay, so the government will paralyze this kind of ratio. It is not actually advisable to draw the current like this. So always it is good to draw sinusoidal current. Okay. So what you are supposed to do here? What you are supposed to do? So what you are supposed to do was, so you can, you know that one portion that becomes reverse bias because I have drawn it. Previously, this is input voltage, this is a output voltage. Only this portion only diode is forward bias, right? You have seen that because only because in that portion is there diode is forward bias. Therefore, current we are drawing like this. But instead of that, what we are doing now here was, so you are taking you are actually rectifying when you are giving the boost converter. You see this part? This is a boost converter. Correct? This is a boost converter. So during this period, whatever we have discussed previously, during this period, so we basically can boost the voltage till here and then try to send some current. Previously, we have told in this period the diodes are reverse bias, or it is not a forward bias, so the current will not flow here. That's what we have told previously. Because at that time DC naught is greater than V input voltage. Though it looks like it's a forward bias, but because of the balance of the capacitors, so the current will be like this. There is a zero current. But once if you boost, so what you can do is, though the voltage is here, you can make higher than this voltage and see that some current flows. You see that some current flows, okay? Because if you make higher than this, then you can ensure that the current is flowing, okay? That's the basic principle of this single phase rectification. So what we do was, so whatever the waveform comes here, we basically boost. But the control is little different. So it is like this. We have seen that in case of boost converter, when the switch is closed, VL is equal to VL. When the switch is open, VL is equal to VL minus V0. You have seen. That means if the switch is closed, delta E is positive. The switch is open, delta is negative. We have seen in the converter discussion, right? So what we actually do was, here, imagine that I require this current. This is the magnitude of the current I want. Okay. So we create a small hysteresis band in both directions. Hysteresis band. Okay, we create a small hysteresis band. Okay. Now I turn on the switch. See here, I turn on the switch. If I turn on the switch, current rises. You know the current rises. Delta is positive. Then if I switch off, current decreases. Switch off, current increases. Switch off, current increases. Okay. So what will happen is it follows this pattern on off, so that if imagine that the switching frequency is very high and if the band, distance band is very small, what will happen was the waveform looks like this. Very small, it looks like exactly a sine wave. It's small, the content is very small. The delta E is very small, so it looks like very close to sinusoidal. Okay, you got it? So this is how we do. Once again, what we do was, so we do a hysteresis band. Once it is touching upper hysteresis band, it will turn off. Once it is touching lower hysteresis, it is turn off. Okay, like that, we ultimately what will happen? The frequency is very high. It follows whatever the reference signal we are giving. Because the reference is sinusoidal, then the reaction signal is also following a sinusoidal. Have you seen the anywhere hysteresis control practically? Have you seen hysteresis control? Especially the hysteresis, if you see air conditioners also, in case of air conditioners, previous type of control, now not with respect to inverter control, but without inverter control, we previously use air conditioners, right? So in that, what we do was there is a compression. Okay, you know that there is a compression. So compression has two signals, either is on or off. There are two signals. Now imagine that 30 degrees centigrade is there. Room temperature is 30 degrees centigrade. But our set temperature is, for example, 24 degrees. What will happen? So the compression will be on, and it will be on till the temperature reaches some 20 degrees. Though our set temperature is 24, plus or minus 2, band generally we will keep, manufacturers will keep plus or minus 2. Because the 24, 26, we don't feel that much difference. So, previously 30 degrees, previously it was 30 degrees. Okay, when the compression is on, we come to some lower loop, which can be something 22. But our set temperature is 24. What will happen was here the compression again will be turned off. Like, once we sense the temperature, if it reaches 20 degrees, we will turn off the compression. So once the temperature is compression start up, again what will happen? The room tries to get to its room temperature, I mean normal outside atmospheric temperature. So it will try to increase like this. But once if we measure the temperature again, if it touches 24, then again what we do was, we turn on the compression once again. Like that, here is the compression on, here is off, here is on, here is off. Like that, the compression will be on and off, though the average temperature is kept at 24 degrees. This is how the general compression works. Similarly, here also, once the switch is turned on, delta E is positive, when the switch is turned on, delta E is negative. So if the sinusoidal is the reference signal, then you take hysteresis upper and hysteresis lower band, then you turn on and turn off following the hysteresis band. Is it clear? Following the hysteresis band. So if your hysteresis band is sinusoidal, then you will actually understand the average value to be a sinusoidal wave, so that you can reduce the harmonics. See, previously the current is like this. See, this is actually more the frequency if you are doing, this is how the shape is. But without this, you will have a shape like this. So this is more sinusoidal, this is a better curve than this curve. Okay? Is it clear? That is how we are able to change the, otherwise we are able to draw the sinusoidal curve from the this is called pulse curve. This is called pulse curve because we are applying PWM. The same thing, both circuits are same. Operation wise, both are same, but the only thing is here we have taken diode and then one booster. So here what we are doing, here we are doing diode and then booster. But here, so this T1 and the T4 will boost in positive direction, and T2 and T3 will boost in negative direction. Okay? So both are actually principally they are same, but only components wise they are different. Okay, so let us 2 minutes I want to give a break because this is another important concept. If you understand this, then whatever reactive power compensation or solar peaking integration or charging the battery, that is called grid to vehicle, discharging the battery, vehicle to grid concepts, all are linked to this slide. Okay. So any questions you have? questions. Because you don't have questions, I have questions. Please stand up. You tell me what is the requirement of grid synchronization? Like you have a already grid is there. Now I want to synchronize that grid. What will you do? I have a grid, but I think you have studied grid synchronization. One experiment is there, right? Synchronous generator. Is there? It is there or no? No. No, sorry, zero. Grid synchronization. Have you done? Second year. If I may. Third year. Have you done? Grid synchronization. Studying. Nobody has studied. Lab, at least, you don't offer any experiment. Please say, what did we do? What did we do? What did we do? Integration. What are the conditions for synchronization? Have you done synchronization? You done, right? There is a lab. So alternator synchronization. So, but no, using proper terminology. So for proper synchronization, the frequency of operation. So we need to see that the frequency and synchronous frequency they should be same. Then voltage, they should be in same phase, correct the same phase. To detect the same phase, what we do? What is it? How is it synchronized? Have we heard about cycloscope? Cycloscope. Two bright, one dark light metals. How do you synchronize the generator? students of NRI? Yeah, NRI. Who are the students of NRI? Please raise your hands. You are also NRI. Whether you have any habit of raising your hands, don't have otherwise. Now who are the minors? Who are third years? Okay, you have completed experts, right? Okay, so in case of synchronous generator, first of all it should be leading, like E and then we assume that the grid is lead angle. Then the rotor angle should lead with respect to the grid frequency. Okay. Now, so the same concept actually here also be applied. Okay, so especially just imagine that in case of synchronous generator, okay, if you want to connect to the grid, the frequency operation should be same. So our frequency is assumed 50 Hz. So here also we need to operate the frequency of converted to 50 Hz. Okay, that's a power frequency. Then there is a switching frequency also. The switching frequency usually we take 11 times to 21 times to the frequency of operation. Of course, it depends. You can make higher frequency also operation so that you can reduce the L and C frequency. But anyway, so this is a what to say? This is a complete picture of battery to grid or grid to battery, or it can be a solar also. So imagine that this is a DC grid. So don't bother about whether it is a battery or capacitor, whatever it may be. Just consider that this is a simple DC link. Okay, this is a DC link. Then we already told about this 4 voltage, like you get VDC or minus VDC based on the switch on and off. Okay, and we also seen that here you will get a sinusoidal waveform. If the sine reference waveform is given, then you will get a sine waveform. So this potential is, see here, this is sinusoidal, right? This point, Vm sin omega t is the grid voltage is sinusoidal, the inverter voltage is also sinusoidal. So what we can do was, you can write like this. This is V grid, okay, and then L, and this is V. So what is why we are taking, though basically V is a grid voltage, it's a sinusoidal voltage, but here I have indicated the polarities plus minus and plus minus. What is the meaning of that? What is the meaning of why keep the polarities for the AC wave? So to talk about whether that is positive, whether it is in positive mode or negative mode, we can indicate with the plus or minus. So now just take this. This is a VG and this is a V inverter. Okay, V inverter is also sinusoidal, average current. Because of average sense, V inverter is also sinusoidal. Now I am assuming that this is a current I. This is ISA or I just assume that this is I. So all of you look into here. So once if I assume that this is I, okay, so V grid I am taking as a reference, that this is a V grid. Okay. If I want to draw the current, as I just imagine that let us say like a rectifier operation. Rectifier operation is whether it is V2G or G2G. Rectifier operation means the grid should be, grid should charge the battery. That means the power flow is from grid to battery. So that is G2B. So for a G2B, if the current is like this, okay, what is VL? Tell me what is VL? This is a plus or minus VL. We know the current I. Where is the direction of VL? You know the current of inductor. Where is the direction of the voltage? No, in case of inductor, I know the direction of the current. How to find the direction of the voltage? Inductor. Voltage leads the current by 90 degrees. Current lags voltage by 90 degrees. So if this is I, this is VL. Okay, if this is VL, I can put the VL here. And this is V. Okay. So this magnitude depends upon modulation index, this depends upon phase shift. So with respect to modulation index and phase shift, then we can actually change the V inverter. Once if I change the V inverter, if we are making the V inverter with phase shift of this and the modulation index in M, I put like phi 1 and M1. With the phi 1 and M1, then we can draw this much value. Okay. So once again, what we do was, so the grid voltage is AC voltage. Okay, and then we assume that the inverter voltage also saturation voltage. Then, so if you represent the equivalent circuit, then we get like this VG, E inverter, and then this is the inductor voltage VL. Okay, we are drawing, our intention is to draw the current. Then we put the current in this direction. Okay, then we calculate where is the direction of VL and where is the direction of V inverter. So if you create a phase shift of this much and this much, then we draw the current diagrams. Okay, so we first we assume the direction of the current, and then we will come the current later. Okay, by giving a proper M1 and phi 1. Okay. Similarly, you take the other case. Just imagine that this is V grid. Now I want to send the power from vehicle to grid. Vehicle to grid means we have to supply the power to the grid. Then IG should be in opposite direction. IG means in this direction. This is IG, opposite direction. If IG is in this direction, what about VL? VL comes in this direction. This is VL. If this is VL, like I can put VL is here, and this is V. You apply KVL here, VG is equal to VL plus V. VG is equal to, or VG bar is equal to VL bar plus V inverter bar. Okay. So like that we can actually do the inverter operation like this. But here, this is a phi 2 and the modulation index is given by M2. That means here what we are doing was, we want to draw the current from the grid actually, some current. So from the vector diagram, we actually find out where is VL and what should be the corresponding modulation index, what should be the phase angle. Then if you apply the modulation index and phase angle, then we draw the same current. So similarly, if you want to inject the current also, using the phase angle, we try to identify where is the inverter voltage. Depends upon the inverter voltage, then we try to give the proper modulation index and proper phase shift. But here we need not give directly like this, but there is a lot of theory has about using a DQ transformation techniques. Of course, I don't want to deal much, so I want to stop here. So this is somehow the waveforms of synchronous currents and grid currents, and then you see the inverter voltages. So, because now what we discussed here is about some of the inverter and digital converters which we have just highlighted. But see, if you want to build any physical inverter or digital converters, we have to choose different elements like inductor element, capacitance elements. For a switch MOSFET or IC we usually use. So for that we have to choose whether what is the blocking voltage, how much current it has to flow. What should be the operating frequency? Then what is its on-state resistance? What is its turnoid or and then thermal resistance? These are some parameters we have to look into when selecting the MOSFET or IC. So I have shown you one of the data sheet like IR of 540, IR of 530. So you can see the MOSFET that we can whatever IR of 530 has a blocking voltage of 100 volts and the drain current to 30 amperes for IR of 530, And similarly, the RDS or which I told you is 0.077. Then turnout time is 28 nanoseconds and turnout time is 30 nanoseconds. Similarly, RP, the thermal to phase junction resistance is 3.3. These parameters are very important out of a data sheet. Other parameters are they have less impact on this. So this is a typical MOSFET IGB data. So usually there are two types of circuit. So one is a power circuit, other is a control circuit. So power circuit means IGBT switches, MOSFET, and then the power supply load. Whereas control circuit means to give a proper PWM between gate to source. Between the gate to source we apply some PWM, but microcontroller actually we give the PWM. But microcontroller voltage levels are 3.3. But gate to source voltage levels are 15 and 0 for IGBT and 12 and 0 for MOSFET. So to do that, we need a level shift IC, and similarly there is an electrical isolation also required between gate circuit as well as control circuit, power circuit, control circuit. We need a electrical isolation. So that we use optocouplers. So this is one optocoupler in 250. And similarly, to create a power supply like 12 volts or 15 volts for linear power supplies, for isolation power supplies, especially for driving the gate. Then this is a kind of a power supply. It's a schematic diagram I showed you. So 780552 is equal to 5 volts. 79055 is minus 5 volts. 7812 4 volts. 7912 minus 2 volts. Similarly, if I want to get a variable DC voltage, then LM317 is IC we can use. And some of the inductors here I have shown you, especially for building the buck boost converters, buck converter boost converters. There are a couple of inductors. They depends upon the frequency of operation. We need to choose a proper L values in inductors. Sometimes they are like a flat core inductors, iron core inductors, silicon steel inductors. Okay, and ferrite core inductors. These are some different types of inductors. Okay? This is a picture actually different types of inductors. And then somebody who wants to like implement in a hardware, then couple of softwares are available, like Proteus software is there, and then Power ECM is there, then PCB making, bit tracing. These are some softwares available. Texas Instruments design tool is one best example. If somebody wants to design any converter, simple, for example, boost converter, you type boost converter T8, Texas Instruments design. Then you can get lot of design resources. You can open it and then try to see how basically the boost converter can be built, or buck converter can be built. So that means how to select the value. So what parameter we have to take value, how to which capacity we have to use. The specifications or details can be available in the design tools. Then some things like the PCB, like we need to sometimes we need to do PCB fabrication at your lab. You can do actually. So for that we need to know about how to do the PCB. There are online resources like ATAL. ATAL is one online PCB making tool. Like somebody can open ATAL and then try to build some PCBs and then take a print on the laser print. And then there are copper tractions. This is a copper traction. This is a copper traction. So on the copper track sheet, you can take a printout of that, and then you can use ferric chloride to actually what it happens was, if you put a laser printer over the PCB flat sheet, this is a copper. The ferric chloride and water if you mix, that it will absorb the copper. So this material, whatever the printed material will not stay, the other materials will go off. So then we can actually do soldering. This is a typical PCB layout. Just for your reference, I just gave this. Right. Of course, as I told you, like even in case if you are able to do it also, there are some sources like chip craft technologies, RGS, ink ocean. Some sources are available. Like if you should have interest to do a simple buck converter, there are a couple of sources available online. You can actually give the circuit diagram. They can print and even solder a part wise also. They put all the internet switches in everything they do it, and then they give go directly to you place. Then some of the equipments like it's not very dynamic. Then we have to wire strippers, then use capacitors, LEDs, all are very important, especially for building the hardware. Then you know that as I am talking that sensors, because they are especially for microcontrollers, somebody should give the data. I think you might did some projects for Arduino also, like humidity sensor, so and so. Okay, to check whether the soil has humidity. Some projects I think you might did that, some of you at least. So there what we do was the sensor is the one which gives the input to the microcontroller, and then we can take action against maybe like turning the motor on. Some of you students might read the humidity sensor based irrigation. Okay, where we sense the humidity and then we turn on and turn off the fan. You might have done right. The same thing here also we can do. We have a voltage sensors. Most of the times what we do in case of inverter, whatever the converter we take, we take voltage measurement, we take the current measurement, we take the speed measurement, and then we give it to the microcontroller. So we require some sensors, okay? So here the most popular sensors are MEM sensors. MEM LV25P is a voltage sensor, MEM LA25 is a current sensor. Using that we can actually sense the actual voltage in there. Similarly, you can also go with the low cost sensors like ACS712. Okay, is one low cost current sensor. And similarly, like both current and voltage of AC can be measured using this module. Okay, this module. Okay, and so some of the interfacing devices like we need sometimes keypad, touch device, input switches. Then the main brain of all the control logics is a microcontroller. Sometimes Arduino, I think Arduino, then Arduino, Nano, So, but most popular for power electronics applications Arduino DUE. Among all Android Arduino boards, Arduino DUE is the most popular for power electronics applications. Okay, similarly we have Texas boards, we have STM microelectronic boards, we have Raspberry Pi. So not only this small, we have many other 10C boards, C Studio boards. But apart from this, some D-Space boards, very costly boards, D-Space, FPGA controllers, or Texas System boards, Typhoon Gate boards, HI, hardware in loop simulation tool. Then we have Opal. Okay, so many, lots and lots of industries has developed a lot of things for controlling the power electronics semiconductors. Okay, basically is one real-time controller. Yeah. So, thank you. If you have any questions, I would like to answer you. Any questions? Okay, I'll present few things for we have a DSA and especially for you, because you are electrical engineers, so few things are very important. So one is if you take a general UPS, okay, your father also knows what is UPS, correct? The father also knows what is UPS, and what is the extra doing. Like because you are being an electrical engineer, you are getting some degree. What is it more than him about it? He also tells if he wants to purchase, he can go to the market and then he will see okay, give me 10 hour backup UPS. If you ask for 10 1 kVA load, I need 10 hours backup. Then he will give But how do you judge? Because being an electrical engineer, whatever he gives, how do you judge it? How do you judge? So you need to have more information than what your father does, what your father knows, or whatever the family members knows. That means there is a core understanding of how the inverter works, what is meant by proper harmonic distortion. That after seeing the data sheet, you should relate that okay, this has OPSD, this has SPSD. Like that, some additional parameters you should know. See, if you talk about a normal person who don't know about drawing, everyone knows that we have one pencil, HB pencil, correct? But who knows drawing, they know many types of pencils. Like they'll ask about 2H pencil, H pencil, HB, 4HB. Like lot of things are there who does drawing because they are specialists in that. Similarly, being electrical engineering, you know more than what general we do. So I request like you, whenever you are going to lab, you just look into the item and then you should have a belongingness. Okay, that is my item. That is electrical instrument. Okay. Okay. Any questions you have? Okay. We have one lab called the DSI lab. So it is sponsored by government of India, DSI. So that is especially like you, those students who are interested in setting up a startup in the area of renewables. Then you always come to us. So always the gates are open to you. In case if you want to build in a startup in the areas of electrical vehicles or renewables related to electrical, whatever the field it may be. So we have a good facility, especially for electrical people. Like if you want to do in terms of power converters, like we have a lot of stacks. Single switch stacks are there, multiple switch stacks are there. Then we have 4 bridge stacks, SCR devices, gate drives are used, number of devices are there. We have programmable sources, we have electronic loads, we have real-time controllers like we discussed previously. Right? So many apparatus, so many equipment are there, especially for batteries also, battery testing, discharge testing equipment are there. Okay. If you want to utilize this, you can comment them. So you can do some internships also at our place. Okay. Only thing is you have to work hard at that place. So, any questions you have? I am expecting some at least one question from you. Nobody is asking any question. Any questions?
Any questions? Any doubts?
we use DC converter. So that operations use. Similarly, for a traction to do VPF control. VPF control. So that is why we talk about inverter. Then, especially for charging, we need to draw types of currents for charging. Okay, then we have discussed about how, like how small has a peak current step, how the rectifier was modified through PW, so that we can rectify all sides of the current. This can be used in this system. Okay, that is also smart charging. Similarly, we discussed about vehicle battery and digital. So all of our
Thank you, Shankar sir, for spending your valuable time for us and giving a very informative lecture for everyone presented here, sir. So now I'd like to invite our principal, Dr. C. Nagavaskar sir of NRI Institute of Technology and Head of the Department, Controller of Examinations and Coordinator of this ATAL FDP, Dr. N. Sankar sir, to please illustrate Shankar sir.
Study.